All right, thank you, Chita. Without any delay, we'll start our first talk from Carol. I'll let Tejas introduce you.
Awesome, yeah. So yeah, it's my pleasure to introduce Karel Lenk. So Dr. Karel Lenk is a research scientist at Google DeepMind. He completed his PhD from University of Oxford and master's and bachelor's from the Czech Technical University in Praha. During his PhD, he made important contributions to different aspects of image representations, starting from feature extraction and descriptors and matching. So recently, he has been one of the key core contributors to Flamingo, which is a family of vision language models that can learn from a small number of examples to adapt to novel tasks. So today he'll present existing approaches to vision language models and tell us about Flamingo. So I'm very happy to introduce him as the first speaker of our workshop. The stage is yours, Carol.
We can maybe test to see if the online attendees can hear us.
Yes, so there is some feedback from the author, from the participants online. So if you're kind of closer to the laptop, I think we can hear you clearly. But if you move away, then it's a bit patchy.
Okay. I think what he's saying is for the speaker, if we can get closer to the microphone, and online attendees can hear you better. All right. Look forward to it.
Hello, I'm Karel. I'm coming from Google DeepMind, which is the name we use right now. And I'm going to be talking about evaluating and training large language models with vision capabilities. Most of the work which I will be presenting was published in the Flamingo paper, which was published in NeurIPS last year. And as you can see, the paper was made by a lot of authors. Originally, Jean-Baptiste was to present this talk, but unfortunately, he wasn't able to attend. So I'm here instead. So I will first start by introducing VLMs as kind of like the broader category of models, which try to adapt to large language models for visual tasks. And then I will go a bit more detail into the Flamingo model. And finally, I will introduce our evaluation protocol, which we used for evaluation of the Flamingo model. So VLM, you probably heard a lot of different terms for it. For example, the workshop abstract calls it just V plus L. It's a wide category of models, which you can generalize as any sort of model which takes as an input vision and also a text, and then does some magic and either outputs a text or solves some particular task based on the vision and text. So in this example, it's, for example, a question about the cat in the image, and the model can answer you that question. The core idea of this is that this simple interface allows you to solve many downstream tasks. Another way how you can look at it is that VLM is basically a form of a bridge in between the vision model, which is basically the perception. Then the language model itself actually specifies the interface. But it's not only the interface, but in the era of large language model, it sort of provides the reasoning part. So it can answer some common sense answering and so on. So before I will delve into the different categories of those models, I think it's important to reiterate the well-known paper of attention is all you need, which kind of defines the transformer model. The original transformer model was consisting of two different parts. The first part was encoder, which is basically a part of the transformer which has full self-attention without any masking. This basically means that it can see every input token and can attend to every input token as well. Example of models which are encoder only is BERT or various VITs. This is important especially for the vision because there is no order of the vision tokens, and it's really useful to actually be able to attend to everything in the full image. Then the output of the encoder is being fed into the decoder, which again is a similar architecture but has two differences. One is that instead of self-attention, we actually use masked self-attention, which basically uses a causal mask, which is this triangular pattern. And what it does is basically that any text token can attend to all tokens which came before that, but cannot attend to anything from the future. This is important for kind of simulating the sampling process, and also then it allows basically the teacher forcing in some way. Example of this model is the GPT models, chinchillas, which are from DeepMind, or the bulb models from Google Research. Another thing which is in the decoder model is that it uses cross attention, which is how the output from the encoder is being fed to the decoder. Just to reiterate, the transformer model from the attention is all you need was actually both of these parts together. So the first class of vision language model, or one of the first which emerged, were the contrastive models, which is really simple because you literally just take two encoders, one vision encoder and one language encoder, and then you contrast the representation which these models provide you. This has the advantage that with the contrastive loss, which is visualized here, you actually generate a lot of positive and negative samples. So if you have, for example, a batch size of 256, you kind of magically have 256 positives and 256 squared minus 256 negatives. It is trained in general on an image text label. And as you can see, there is a lot of different papers which actually use a similar method. Because these models don't really provide you anything but the representation, they are generally the most useful for image classification and image retrieval, and they are quite good at that as well. The second class of models which emerged back in 2019 are the BERT-like models, where BERT is an encoder-only attention model, which is basically trained for providing a good language representation. You have sort of like two different categories of these models. One is a single stream where you treat the images the same way as the text tokens, or you have dual stream where you kind of like play with the cross attention and try to combine the text and images. They very often depend on object detectors, and their disadvantage is that they can't be really used for sampling because BERT itself is mostly used for providing a representation. So you typically fine-tune it for the downstream task. And again, there is a lot of examples of these models, and I'm sure I'm not listing all of them. However, then we have this kind of like more general category of VLMs, and those are the VLMs which can actually provide you a sample of text. And once you have this, the model can kind of automatically solve a lot of different tasks. It can do question answering, it can do captioning, and what you can imagine is also like classification, which we do with Flamingo. And as you can see, there is also a lot of examples of these. Probably the GPT-4 falls under this as well, though there are no details about the particular implementation. So one example of this model is actually SimVLM, which came out last year. And this model basically uses the original transformer architecture. So you have a transformer encoder, which takes as an input both images and the context. And then based on that, it conditions the transformer decoder where you can sample the answers. Everything is trained together. And advantage of this architecture is that you can actually use the text, for example, a question, to basically attend to the image itself. So the model can kind of understand where it should look. One slight disadvantage of this is that it has a strict division between the input and output, so you can't really use it for a chat interface. So you would use the decoder on the models like GPT, for example. So my colleagues from Google Research take it into the next level with the poly architectures, which are again encoder-decoder architectures on much larger scale, and they currently hold state-of-the-art on many downstream tasks. So what they improved is that they actually train everything on multiple stages across different data sets and different image resolutions. And they also train different variants for different subtasks. So there is a VQA variant, or there's a future variant, and so on. One difference to Flamingo, which I will talk about a bit more later, is that they actually scale together both language and the vision backbone. But again, because it actually uses the encoder, it has the disadvantage that there is no fixed order of the images in the encoder. So when they want to do a few-shot reasoning, they actually have to adjust the attention mask to basically increase the attention to the query image, which is the image we are asking question about. And they do it by simply multiplying the attention mask of the input query. So this is a thing which doesn't really is a problem for decoder architecture, where kind of the first work which we published at DeepMind was the frozen model. And this uses the simple idea that you can actually freeze the language model and basically treat images as different variants of the image tokens. So in this case, we basically feed the vision features as a different embedding. Because first thing you do in language models is that always you take the tokens and then you have basically embedding layer, which just maps those tokens into learnable vectors. So this has an advantage that you can, out of the box, basically solve many tasks, and you can also feed the model with few-shot context, as in this case. You can basically teach the model here in the context, what are the different types of apples, and then ask, what is the type of the apple here? And it sort of like knows already from the context what is exactly the textual output it should give you. And that brings us to the Flamingo model, which is basically an extension of the frozen model. And the major differences here is that it's uses a completely different architecture when it comes to adapting the language model. So similarly as the frozen, it's decoder-only architecture, and we freeze both the vision and language backbone. Additionally to frozen, we support videos as well. So here is an example of inputting a video, and you can see that the model can actually correctly answer that the golf player actually falls after he hits the ball. But because it is a decoder-only architecture, you can actually have a chat with the model as well. So in this example, the model was conditioned to love giraffes in the input context. And as you can see, you can actually input single image, have a chat about it, and then actually continue directly by uploading another image, and the model still remembers the context from the past. So the core design philosophy of Flamingo when we started developing it was that we wanted to have a state-of-the-art generalist vision language model, which can be rapidly adapted to different multimodal tasks we have future learning. That means that we basically wanted to create sort of a foundational VLM, which is trained on large data set and then can be used without any fine-tuning or any adaptation to a lot of downstream tasks. So, as I said, it can be really quickly adapted because it doesn't use any fine-tuning. And only thing which we do for the new task is that we provide some examples from the training set in the context of the model. So here's a overview of the model architecture. It's maybe a bit too much, but I will slowly go through the individual parts of the model. So as the vision backbone, we actually use the contrastive retraining, basically clip-like training on a large image data set. And instead of VIT, we actually use the variant of NFNet, which is basically a CNN without any batch normalization. As a paper published by Andy Brock. And after the pre-training, where the text encoder is actually BERT-like model, we use just the image backbone, which provides you basically a set of image representation, which we can then feed into the final model. In particular, we actually remove the pooling layer, so we are working directly on the features. So we have input around 8x8, like width and height. Then one major improvement, which was actually necessary to be able to process videos, is that we use a perceiver resampler. Perceiver is another paper from DeepMind, which we found really useful. And basically what you do here, it's a attention model where basically you feed the input to the model as a cross attention. And then you use learned latent queries as the input. And the major advantage here is that you can actually select how many latent queries you're going to use. So for example, for the video, we have 8 frames of video, which we then pass to the vision encoder. And we end up with this gigantic tensor, which is basically, actually, it was, if I was calculating correctly, it was 28 width and height. And it has also 1536 channels. And we feed this into the resampler, and we basically select that the resampler has only 64 inputs, no matter whether it's a video or a single image. And then with the resampler, which is trained from scratch, basically, we can get this representation, which is much smaller and it's much easier to use as an input to the language model. One useful comparison for this is that the debtor object detector works in a similar way. So then a second magic trick which we used is this method which we call gated cross attention, which is basically a form of model surgery where we implant basically the vision features into the language model. And we do it by the way that we add into the language model a cross attention model, cross attention layers, which are then followed by TAN-H gating. And the TAN-H gating has learnable features which are initialized in the way that by default, it doesn't pass any information. But as the model starts training, those variables start opening up. And then basically the model learns sequentially how to adapt the language features based on the vision features. Because all the tasks we train it on, it needs to use the vision features in order to answer the questions. So the data sets which we used were basically just 3, which is a big difference to the poly, where they use much larger quantities of the training data sets. And we just used the interleaved data, which we call M3W, which is basically 44 million scrapped web pages with interleaved text and image. On average, each web page has 4 images. And in this case, you kind of like have text, and then in the text, you have the position images. Then we used additional 2 billion image text pairs and 27 video text pairs. Both of these data sets we scraped for the paper. Additionally, it's important to point out that the biggest flamingo, which we use and has 80 billion parameters, has been actually trained for 15 days on 1500 TPU chips. So even for DeepMind, it has been actually quite an extensive project to be able to run this. So for the Flamingo family, we train basically, or we present 3 models in the paper. So we have the Flamingo 3 billion, then we have the Flamingo 9 billion, and then the main Flamingo, which is 80 billion parameters. And what we did is that for all these models, we actually kept basically the size of the vision encoder and the resampler the same. So most of the parameters of the model are actually in the language model. When it comes to Pali, they actually have shown that you can gain significant improvements if you scale both the vision and language backbone. So now going to the evaluation. And I think the evaluation, especially for the Flamingo project, was relatively complex because we sort of like had this much larger task at hand in the beginning, because we wanted to generalize not only across the splits of the data set, but also across different tasks. So when it comes to standard computer vision data sets, since the emergence of the machine learning in computer vision, it has become kind of a standard that every data set is split into train, validation, and hidden test set. So you take your training split, you train your model, where you obtain your trainable parameters, and then you use the validation set in order to select the best performing model. So basically what you do is that you impose the validation set as hyperparameters on your model. And then once you are done and you have your promising model, you evaluate it on the hidden test set, ideally, which is done usually through evaluation servers, and then you report your state-of-the-art results in your paper. What changed since the emergence of deep learning with basically the AlexNet, which was introduced in 2012, was that you actually used a big pre-training set, where for AlexNet, it was actually the ImageNet data set. And then you apply the pre-trained AlexNet on existing downstream tasks. So you basically, again, you have your model with the pre-training parameters, you fine-tune it in your downstream task, you do the hyperparameter selection on the validation set, and then you get your results. One important aspect here, which is sometimes forgotten, is that you need to make sure that the test set does not overlap with the pre-training data set, which is usually a relatively difficult task to do. Things get a bit more complicated once you have actually multiple downstream tasks you want to fine-tune. Because if you fine-tune on the first task and you select your hyperparameters, and then you take your pre-trained model and you try to fine-tune on a new task, even though you have a different fine-tuning parameters, you still made a decision for the hyperparameter selection on both tasks. So you end up basically with a model which has the hyperparameters from both downstream tasks. And for Flamingo model, where we use, I don't know, 15 downstream tasks, this can get really quickly out of hand. So what we aim for Flamingo in the evolution protocol is to assure that we have as big independence on the downstream tasks as possible. So the way how we do it is first, we get rid of the fine-tuning phase. We just don't do any fine-tuning on the downstream tasks. And then we take a subset of representative tasks. In our case, it's just 7 tasks, which we assume to be the dev set. And that's the set of tasks on which we are going to fine-tune. Additionally, we create a subset of the training set, which we call the dev query, which we use for the online evaluation. And similarly, we also fix the support sets for the additional sets. So we have the dev support, validation support, and test support. The reason why we fix the support set, which is fed into the future prompt as a context, is that we want to limit the variance of the results which you obtain on the different evaluation sets. So here is an illustration how it looks. Support set is being used basically as the future examples, and then query set is being used as the example on which we ask the question. So then when we are training, we basically use the dev set to evaluate the score and be able to select the hyperparameters. So kind of like the most promising model. So ultimately we end up with the pre-trained parameters and then the hyperparameters. The fact that we have only 1,000 dev query examples means that we actually have really fast online evaluation. So we can evaluate during the training and see how it develops and potentially stop the training early if the results aren't as we would expect. But because the hyperparameters are all based in the training set, it actually, we are not biasing into any other subset. And we already use the support examples from the training set, so it's unavoidable to have this. Then, once we have a promising task, we actually used the validation set for internal leaderboard. So basically, only once we had a really promising model, we evaluated on the validation set, which took a while because some of the validation sets are really large. We also measured performance as the average relative to state-of-the-art performance, which basically gives you a single number you can track the models across. And then when it came to writing the papers, we evaluated our model on the hidden task, which the model had never seen, and we also never saw the results on these tasks. So there was no bias towards these results. We call this evaluation basically a true future evaluation because there is no influence of this task to the rest. So these are the benchmarks which we used for evaluation. We split it in half for image benchmarks and video benchmarks, as you can see here. But additionally, you can split those between open-ended and close-ended tasks. And here is the visualization of the tasks, which we had as a part of the development set. The difference between open-ended evaluation and close-ended evaluation is that for open-ended evaluation, you make the model provide you samples, and then you directly compare the sampled string against the label string. So typically you need to do some normalization, such as trimming the string and lowercase and so on. When it comes to the close-ended evaluation, it's a bit more complex, and you need to do this for typically classification tasks. And you do it by feeding basically the prompt together with the class name, then evaluating the model. But instead of sampling, you just take the negative log likelihood of the last token and use that as basically the classification scores of that particular class. And then you basically simply order the scores and evaluate it against the classification labels. So here is the comparison of the big Flamingo model against the state-of-the-art results back in the day, which was April 2022, when we were writing the paper. And as you can see, the Flamingo at the time achieved state-of-the-art results on quite some tasks and improved the previous few-shot, zero-shot state-of-the-art quite significantly as well. And this was all thanks to the big training data set. Similarly, we can also plot the average SOTA against the number of shots and also the size of the model. And as you can see, once you start increasing the number of shots, the performance increases slowly. I think it's interesting to note that this is mainly the case for the largest model, which is kind of a common ability of these large language models, that once you get bigger, it becomes a better future learner, which we observe for the Flamingo as well. Similarly, we can do also ablation study of what is the importance of the individual data sets. So in this case, we show the average score over 7 different benchmarks. And as you can see, the video data sets is relatively the least important. But if you remove it, you actually become much worse on the video tasks. The most important data set is actually the M3W, which are the interleaved image tags. And it's important because that's actually the data set which trains the model to become a future learner and to be able to process multiple images interleaved within the text. Similarly, we can also do an ablation study of what happens if we unfreeze some parts of the model. And interestingly, you actually need to keep the language model frozen together with the vision model. So if you actually unfreeze the language model, what basically happens is that because we don't have any text data set as the input, the model starts forgetting and the performance goes down. Similarly, if we actually train the language model from scratch, the performance is much worse because it doesn't have these billion of text examples to use as the knowledge base. So not only it improves the results, but freezing the language model also makes it much faster to train. And cheaper to train as well, because you don't need to update the language model parameters. Yet you still have to backpropagate from the model because you need to train basically the adaptation layers. So we can also fine-tune the Flamingo model. In this case, I think we are fine-tuning also part of the vision backbone when we do that together with the adaptation layers. And as you can see, at the time with the fine-tuning, we were able to achieve state-of-the-art on some additional tasks. But of course, since then, there has been some major improvements as well. So a lot of the state-of-the-art is now held by the Multi-Modal. We can also try to compare it against the GPT-4 from what was reported on their website. But yeah, those are the only numbers which I was able to find. And as you can see, it's also much better. And I think the biggest difference is the text VQA, where we actually do quite badly when you compare it to even Poly or the zero-shot GPT-4. So we can also look at some qualitative examples. So the model is quite good when it comes to reasoning about the images. So for example, here it can answer us what is odd about this image and just correctly answers that it's not common to see an elephant on a car. Similarly, in this case, it's quite impressive that it actually detects the Canadian flag. Yeah, there's no connection to the location of this conference. Really coincidental. But it can also answer a question about videos. So for example, in this case, it can see that it's actually a puppy being weighed, or it can understand, in this case, that the model, it's a game and the model is about to pick the sword. So now we will quickly go to the limitations of the Flamingo model. So one thing which the Flamingo doesn't do really well, and the contrastive models are much better, is classification. Because we take the negative log likelihood of the language model. We don't do actually any normalization, so we also end up with the NLL being influenced by the length of the class name, basically. Generally, contrastive models are much better on this. Then, similarly as any other large language model, Flamingo suffers with hallucinations, where when it doesn't know the answer, it will just make it up. So here it imagines text on the phone screen, but there is nothing on the phone screen, etc. Flamingo is also quite bad when it comes to spatial reasoning. So it generally struggles about left and right in the image. Similarly, it's really bad on understanding OCR of the input. So the text, that's a thing where Poly is significantly better because they actually have the OCR task as the part of the training set, both for the vision backbone, but also for the final model. And then sometimes the model is actually not really able to understand the jokes in this case. So you have to actually help it a lot, kind of like provide you the answer. So in this case, it's about trying to find out what's funny about this picture. And you really have to like dig deep into the model to provide you the right answer. So yeah, that's about it. Do you have any questions?
Let's open up for if there's any questions, then also Tijas, could you monitor the chat as well if there's any?
Yes, sure.
Thank you.
for the presentation. I was wondering why it's sort of the complex scenes and in what ways.
So in general, my intuition is that because of the perceiver resampler, you basically do form of object detection. So for the 64 queries, it just captures roughly 64 concepts, but that's usually not enough for understanding a lot of the details. Similarly, we don't have any spatial embedding. So it actually struggles to kind of like know where the input is coming from, because it literally kind of like just kind of like gets this list of detections without any location information. So I think it's just a combination of those two factors. I think there probably is, but I'm not aware of any with the top of my head. But yeah, we try to increase the number of queries, but there are kind of like diminishing returns, and it becomes more expensive. And as you kind of like start scaling up, you need to keep things in check. Yeah.
Well, really appreciate your time as interesting research. The first question that I have is, you mean like good qualified data set is really important for training this model? Like, I think like a lot of engineering efforts have been fulfilling on this research. I can believe like the most important parts of like making qualified data set, because we can pull the data set from the web or just invest a lot for annotation, but it's not going to be satisfactory, right? But what's like a method that you have used for making qualified data set for training the model?
Yeah, I'm not really familiar with this part, but we are actually dedicated people who are literally just working full time in collecting data sets, and definitely the Google scale of things helps a lot because you kind of have this like internal copy of internet sort of thing. Then there is a lot of existing infrastructure basically for this type of tasks, so that helps a lot, but it's just a lot of work. So we basically had like around 2 people which were working just on the data set for around, I don't know, 8 months, let's say. So.
Thank you. And my second question is like, what are like visual encoder visual encoder for the understanding the images? Like you said, like use the like learning architecture like clip like contrastive loss, right? And then I just like hypothesize that like providing prior into the image can contribute more understanding for the visual understanding. But do you believe that on the contrary, like providing image or video can also benefit like text understanding or knowledge about it?
So we have the AOPDQA, which is kind of a task is mostly based on the external knowledge. And in case of the data set, actually providing the images still helped. So I think we tried evaluation with the text only, but performance was slightly worse. So I think it does help, but yeah. When it comes to the scale, it's also obvious from the sizes of the flamingo that it's actually the language model which kind of like does most of the work at the end of the day.
Thank you.
I was curious on the limitations that it does not have special vulnerability pattern, but she thought on how to do that, or even at the largest scale of flamingo that we work simply working in.
Yeah, so I think the main reason for that is the perceiver resampler, which is kind of like this forced way how you feed the vision tokens, vision representation into the language model. Similarly, it actually has a bit hard time when it comes to conditioning the image onto the text, because we actually have no communication from the text into the resampler. So basically the detection is always blind to the context. That's a thing which I think Poly improves on, because they actually use the encoder, which kind of like sees both the context and the images together. So it knows what is the important part of the image and what needs to be fed into the decoder afterwards. Whereas in our case, we do like a blind detection, which doesn't understand what is the task at hand. I don't know if it answers your question.
So there's a
I appreciate it, particularly all the details about the condition. I have a couple of questions. There's one is about the beginning below. So you compress all these visual features into a sequence of 64 values. Do you think that do you think that's containing enough visual information for all these nesting clusters? Sometimes you might lose, even if these are continuous value, you might compress too much in proper information. Do you think there are some improvements to vision import that you could make to, let's say, make this visual values more well constant?
Yeah, so later experiments which we run, we find out that improving the vision encoder can still improve the results, similarly as the poly did observe. When it comes to the architecture itself, I think there are different ways how to do it, but all of them have a form of price you have to pay. So far, I don't think we find out a better way than this.
Something like adding some constant test information like part of the there's a visual customization, giving the question starting.
Yeah, we did some initial experiments on this back in a day, kind of like 7-8 months before we published the paper. We got a little bit of improvement on the DQA tasks, but wasn't anything significant. So I think the problem there is that the scale of the language model is so big that kind of like feeding any educated representation back to really big. So like the whole architecture would just become ginormous. So in a way, what the poly is doing with the encoder is maybe the way to go. But yeah, there is a lot of ideas we could have combined, maybe the better representation there as well, I suppose.
Yeah,
We haven't tried it.
Simple way of doing it.
Yeah.
The second question was the language model we're using here. It's is based on the laws. Do you think you can structure that for language model that's really going to instruction software to get that with provide some improvements to
It might have, but then it will also lose a little bit of kind of the common sense reasoning. So that's a thing, for example, which they observe on the Multi-Modal, where you actually train everything together. So they actually don't freeze any of the backbones there. But what they observe is that once you start training on the vision task, the model generally becomes less talkative and provides short answers because there are higher probabilities that those short answers are going to be correct compared to kind of like this long sentence. So definitely you can improve on the downstream task, but we also wanted to keep kind of like the model to be chatty and a little bit of fun to play with.
Yeah, maybe that also could be like a plan where we are on this model with this short answer.
Yeah, so I don't think we have fun data set.
Yeah, so this
follow up with a short question, right? One of those observation you have is especially the example with the Canadian flag. Do you have any comments or is there any follow-up work you guys are thinking about how to make sure that this observation is actually indicating the model captures the concept of Canada and also flag and then Canadian flag. Let's say if we swap the Canadian flag with Canadian something else, will the model still be able to the concept here, or is there any protocols in development to rigorously further evaluate?
Yeah, we didn't do any of this analysis because in many cases whatever you do, sort of like these small improvements. If you just make the model bigger, it just overperforms everything you kind of design. So it's a bit difficult proposition to do this stuff and you don't know how useful it's gonna be. Yeah, we definitely sort of like scaled up on the spatial understanding evaluation and like try to understand what's happening there. But again, getting the model bigger just gives you the improvements. So
There's a question from the Zoom audience. Can you?
Yes, we cannot hear you clearly. Let me try to.
Okay. Or you can just read the question from the chat. Can you hear me now?
Right, that's what I'm trying to do.
Yeah. Just read the question from the chat. That's what I wanted to say.
Okay, I can actually rephrase the which VL task does Flamingo outperform other large like Tally and GPT? Any high level suggestion?
So when it comes to GPT-4, even the reported results which they have on their website, I don't think there is a single task where the Flamingo would outperform it. For Poly, it would be a bit difficult as well. I'm not sure exactly, but more, maybe the AOKV2A be a place where the Flamingo is still a bit competitive because it retains the language model capabilities a bit better than the Poly model does. Yeah, I hope it answers at least a little bit the question.
If you think about it and rated sort of beyond what's recorded.
Yeah, I'm sorry, I don't really know much about this.
Okay, so let's stick to our agenda. Thank the speaker once more. So coming up, we're going to have a poster spotlight presentation.
Yeah, so the spotlight presentations, there are 5. So can you hear me? Yes, sir?
Teachers, could you hear us?
Hi.
Okay, now I think we can hear you a bit better.
Okay, so there are 5 spotlight talks. So some of them might be in person, so maybe we can do those first. So does that sound good? So the first one is from Sachit Menon from Colombia. If he's there in the room, you can.
Awesome.
Yeah.
You have your presentation. You can get your laptop if you are actually on Zoom. And we also have for and then we have visual semantics related suffer from UTC. And we have T2V2T, Yonghi Kim. And we have distinguished rank, Zhang Le. All right, so if you guys could welcome to you. And then we'll get to the talk. Yeah.
Hi, Ejo. It looks like all of them have joined the Zoom room.
Okay.
Yeah. One is remote. I think I don't know about the other four.
The other four are all in person.
Perfect. Perfect.
Yes, you need to enable the screen sharing.
I think it won't let me share while you still.
Can you try now? And maybe you'll need to unshare your screen, I think.
Oh, yeah.
Yeah. Hi, Sachit, you can go ahead. Thank you. Hi, Sachit, you're not audible in the Zoom.
What about now?
Yeah,
Great.
thank you.
I'll just keep going. Now, like we just heard in the previous talk and in many other works, we have all of these really great end-to-end vision language models that can generate all kinds of text from images, and they can give you all of these answers, all of these descriptions, so many things that you would want to know about images. Now, these very big end-to-end models can give you this. So things like, what are the boys eating? Muffins. Sounds good. Where are the muffins? On the table. That's like pretty reasonable. There are a couple that aren't, but sure. How many muffins are there? 2. How many kids are there? Too many. Okay, actually, a couple of those don't seem right now that we're thinking about this. And what's different about the ones that aren't right compared to the ones that are? So the first 2, which we saw that are correct, are kind of information seeking, factual, kind of what we think of as system 1 in this system 1, system 2 dichotomy, where system 1 are these kind of faster recognition, not really reasoning kind of things, versus if you're asking how many muffins are there, you have these steps, right? You need to actually be able to recognize muffins, but also count them. And these end-to-end models, at least like Blip2, and we assume like Flamingo, seem to have issues with this kind of thing. So why not just Flamingo? So not to directly add you too much. But so we have these black boxes, they take image and query text, and you get text out. So some of these limitations of end-to-end are things like math and logic. You don't have any intermediates like explainability. You don't get compositionality. If you have other models that can do certain things, kind of the best you can do is try and tack them onto your existing end-to-end model and train further and hope that they somehow bridge the gap. And hallucination. But what's an alternative? Synthesize and then execute. So as much as I just said about end-to-end models, we're still going to be using those extensively here, but in a slightly different way. What we're going to do here is so our framework is you take a code generating large language model. In our case, we use GPT codex, and given a query, you use that along with an API we provide to write a program that actually breaks down the query into the steps you need to do for that. The query then, you'll apply the function you make to the image using the Python interpreter and the API you've implemented using these other end-to-end models, and you'll get a result. So in more detail, it's probably easier just to show a video, which of course is not fully working. So let's see. I will just go to the website, and that is easier. So let's share that. So, okay, can people see this? Yeah. So how many muffins can each kid have for it to be fair? So you'll have this picture, it'll break it down into this code you make with things like find muffin. First it'll find the muffins, it'll just use the simple Python length function to count the muffins. Similarly, you have to count the kids. Then you recognize that for it to be fair means even division roughly. And Python can already do division really well. We don't need to train on a bunch of 4 divided by 2 is 2, 100 divided by 2 is 50. To get there, it already knows how to do that. So to do this division, we can make this program, we execute this using the best object detection models, the best attribute recognition, all of these other pre-trained models. We can kind of just give to the code generating model as an API and say, hey, don't ask how, but you can find stuff. You can recognize things. We can use all these advances in vision language models and write these programs that when executed give you both these intermediate results you can see of why did it say there are 8 muffins? Oh, these are the things it thought were muffins. As well as kind of giving you more ability to use other pre-trained models as and when you want them, intermediate results, editability if you want to change the program, a lot of other benefits. So please come talk to us at our poster, etc., if you want to hear more about this, and happy to take any questions.
Just to remind everyone, we have a poster session in the afternoon. We have about 20 plus posters will be in the poster session. Thank you. It's really nice work.
Thanks.
We'll have Mustafa.
Hello, everyone. I'm going to present our work on efficient perception augmentation of language models. I'm Mustafa Chakor, and I'm a PhD student at Sorbonne University. Okay. So we assume we have very powerful unimodal models like large language models or LLMs, and the objective is to build powerful multimodal models. So now there's 2 hypotheses at least. The first one is the large-scale multimodal pre-training, where we increase the number of trainable parameters, training data set sizes, and compute, of course. And in this direction, we have a couple of models like Coca, Cosmos, that train 2 billion parameters, Flamingo that trains 10 billion parameters, and up to Palm-E that train up to 560 billion parameters. Now there's another hypothesis, which we favor and we investigate in this work, which is about efficient adaptation of existing pre-trained unimodal models. And here we have also a couple of models like Limeware prompt fuse that train less than 10 million parameters to adapt large language models. We have models more powerful like Blip2 that trains up to 100 million parameters. And hopefully in this direction, we can reach generalist enough multimodal models with way less compute. And our work is here. It's very efficient and it's significantly better than the efficient approaches. But of course, it's still not as good as the large scale. So in a nutshell, we efficiently adapt frozen pre-trained models like OPT on the language side, like VIT trained on ImageNet on the image side, to solve multimodal tasks like VQA and captioning across images, videos, and audio modalities. And the three main contributions are first parameter efficiency, where we train only the linear projection to connect different modalities. We have the late cross-modal interaction, which is equivalent to a cross-attention, but it's more efficient. And data efficiency, where we don't do multi-modal pre-training and we show competitive performance on few-shot learning. I will not go too much into the details. I'll be happy to explain it during the poster session. But basically, we take the last tokens of the last DIT layers, we linear project them, and we inject them in the last layer of the language model. And we directly train on the target data sets like COCO, VQA, V2, and MS4 VTP. So here's the main results on image text tasks, VQA, and COCO captioning. So actually, we compare with three baselines that use adapters, prompt tuning. But the common thing about these baselines is that they take the visual tokens of the last layer of the visual encoder, and they inject them in the first layer of the language models. While with our approach, we have this late cross-interaction mechanism, and we show better performance than all these baselines. We have also other results on generalization, use of learning that you can check in the paper. And to just contextualize the work, so here's a comparison with state-of-the-art approaches that train large number of parameters and do most of the large-scale pre-training. We compare with the zero-shot and the fine-tuning. We are generally better than the zero-shot. Good. But we are not as good as fine-tuning, but we are close like on audio data sets like audio caps and the video data sets. We are not too far from these models. Finally, so let's say there's two main setups. There's our setup where we directly do fine-tuning, and there is the pre-trained zero-shot setup of Flamingo and Limber and other approaches. So for our approach, for the direct fine-tuning, why it's important because it's very efficient. It gives generally better than the zero-shot performance. It's easy to adapt to new tasks, data sets, and new LLMs. So you don't need to do the large-scale multi-modal pre-training each time a new LLM comes. Or actually, if you have also a new task, more complex task, you will need also to do fine-tuning for the pre-trained zero-shot approach. But the main drawback is that you will have task-specific fine-tuning with our approach. So you will have like 4 million parameters to train each time or for each tip. And as general or future directions, we might work on relaxing the constraints by training more parameters, using something better than just linear projection, and working on better cross-modal interaction mechanisms. Thank you.
We have, I think we'll go with all the in-person presentation. Next one is from CVPR.
Hi, it's not audible on Zoom. Maybe you need to unmute.
Session by Fusion and University. The session by Fusion offers the full interaction between video and language, but it comes with a high computation score. And the unit interaction of Fusion is more efficient and effective than the self-attention-based fusion, but it is a one-way interaction. It's video to text interaction without text to video interaction. So we propose a two-way TT fusion. It is an efficient bidirectional fusion, which is more efficient than self-attention-based fusion and more effective than unidirectional fusion. And this is our overall architecture. Our architecture is based on Bindru. It is a super unidirectional fusion method, and we add a text to video fusion on the architecture. And I will first introduce our bypass cross attention for text to video fusion. Our bypass cross attention is a variant of cross attention. If we use cross attention to text to video fusion, the cross attention will associate all frames with a given sentence without the correlation between the given sentence and its frame. As we can see in the below two example, for each query video embedding, it will obtain text embeddings by the cross attention. And if it is relevant, if they are relevant, the query embedding can properly obtain the text embedding. But if they are not relevant, even if they are not relevant, the query embeddings must obtain text embeddings without regard to their correlation. So by considering that only a subset of frames is relevant to the given sentence, we introduce a bypass cross attention, a bypass mechanism in the cross attention by adding the query embeddings into the keys and values of the cross attention. It allows frame features to be associated with themselves in the feed instead of text features if they are not relevant. So as we can see in these two examples, if they are relevant, the query embeddings can attend both text and video embeddings like this. But if they are, if the given sentence and the video frame is not relevant, the query embedding will attend only video embeddings instead of text embedding. And by using the bypass cross attention, we can perform text to video fusion. And the video to text fusion is also performed by using a cross attention and the following self attention in the text embedding. And this is our experiment setup. We follow the standard text to video retrieval training scheme, the pre-training and followed by fine-tuning. So for video language pre-training, we use 363M and Webfield 2.5M dataset. And we fine-tuned and tested on MXRBPT, demo, and active captions for text-to-video retrieval. And this is our main result. Our T2V2P achieves the best result among the method with the same amount of pre-training data. And our T2V2 also achieves better result than some methods with a larger pre-training data. And we also conducted an observation study to evaluate the effectiveness of our bypass cross attention. Our baseline is Bindru, and our T2V2 can be regarded as a combination of Bindru and bypass cross attention. And we also introduced for this observation study, we also introduced naive T2V2 for this observation study. This naive T2V2 can be regarded as a Bindru with cross attention instead of the bypass cross attention. As you can see in the table, naive T2V2 is slightly worse than its baseline Bindru, and our T2V2 is better than both methods. It means that the cross attention is not effective in the text-to-video interaction, and our bypass cross attention is effective in this situation. In conclusion, in this work, we conducted an investigation into the text-to-video interaction, which suffers from an imbalance between the number of text and video embedding. And we have proposed a novel fusion method called T2V2 fusion, which incorporates bypass cross attention. And our TTVT has achieved total text to video retrieval results on MSWT, demo, and active communications. Thank you.
Yeah, let's thank the speakers. I just got instruction from the conference organizers for the poster presentation in the afternoon, coming from between 3 to 4 p.m. Our poster session will be at between number 94 to number 123 at the poster sessions downstairs. Number
Thanks, Rachel.
94 to 123. So you can find one, set it up. Between 3 to 4. All right, so we have the last in-person spotlight speaker. Should be Zhang Lei. Zhang Lu. And just a reminder, after this, we'll have a small coffee break. And coming back from coffee break from 10:40, we'll have Jiaqing Wu from, I think he's with Stanford, talking about this recent work.
Right, it's not working. Let me try this one. Oh, it works. Okay, so hi everyone, my name is Le Zhang, and this our contrasting intra-modal and ranking cross-modal harness tips to enhance spatial linguistic background understanding. This work is collaboration with Rabio and Ashwaya Agrawal. So contrast VOMs such as Clip are good at standard image retrieval, like Coco dataset, but they are not good at aligning details between image and text or fine-grained visual linguistic understanding. Here's an example from AR dataset. Given an image like this, correct caption is the horse eating the grass, and the incorrect caption is the grass eating the horse. Of the same words but different order and semantics. Results show that Clip model is not good at this fine-grained understanding task. We can have similar example with attributes. Both tasks the Clip fails. Clip is trained on image, text, contrastive loss, and Clip behaves like backwards. What this approach do? So here's a model called NakeClip. So to improve background understanding, NakeClip on top of image text contrast loss, it adds strong alternative images and text pairs, and creates hard negative captions to train in image text contrastive loss. Well, we create hard negative captions by swapping the order of nouns, swapping objective, and swapping verbs, and swapping a noun word. So this is an overview of our approach. Last two additional losses use feature harnectives that we generated. We introduced model-specific contrasting loss, which Clip does not have, by contrasting harnective sentences against correct sentences. We also have this rank loss. What rank loss does is it maintains a minimal ratio between correct and harnective image text pairs. We have more details on how this works and that on our adaptive threshold mechanism. Check it on our poster or paper. And we have tested our method on 3 fingerprint evaluation benchmarks. That's ARO, WOS, and WELL checklist. And results show that our methods outperform pre-op previous methods. Here are some examples. I'm not going to introduce them in detail, but you can check them on our poster. So here's some summarization. First, connectivity can improve fine grained understanding. To make it work better, we propose 2 losses: intra-modal contrasting and cross-modal rank loss. And this is our poster. Thanks.
How about the hard-active image?
Hard-active images. There are some works to generate hard-active images using diffusion model, but currently in this work we didn't do that.
You see it.
Yes, it could help. Yeah.
Thank you.
Thanks.
All right, so our last poster spotlight is visual semantics relatedness from Amit Sabur from UPC. I think he is going to present it remotely. Let me set it up.
Yeah, he's in the Zoom room. So Ahmed, if you want to share your screen, perfect. Thank you. Yeah, you can go ahead and unmute.
Amit, can you hear us? Could you try to say something?
Okay.
Okay, so please go ahead.
Okay. Today I'm Ahmed Sabir from Universitat Politécnica de Catalunya, Barcelona. Barcelona, Spain. Today I'm gonna present our work, a visual semantic dataset for image captioning, which is a joint work with Francesc Moreno from the UPC. So learning the semantic relation between text and object or its surrounding environmental visual context is a crucial task in visual grounding, like mapping the visual information to a higher level understanding. And while there's some publicly available data set for image captioning, none of them include textual level information in visual context in the image. So in this work, we propose a visual semantic data set for caption pipeline. From each image, we extract 3 types of information: image net classes, COCO categories, and for rare out-of-domain classes, we employ zero-shot clip. Here an overview of the dataset. By leveraging the semantic understanding between the object and the caption, we managed to filter out non-related object in the image, and we have more focus and relevant object caption dataset. So the main idea is to overcome the variation in confidence level among individual visual classifier for object and image, as shown in the figure. For each classifier give different degree of confidence regarding the object and the image. And we use the human annotated COCO caption dataset to extract the visual context. By leveraging the human annotated caption as a reference, we establish a semantic relation to end and the object in the image through similarity score. And we introduce 2 datasets: visual context with similarity soft label, and object and caption overlapping visual context dataset. So now let me dive in the filtering process of this dataset over the top 3 object extract from each image: a threshold to remove object with low score, with low confidence, and word level semantic alignment with gloves to remove duplicate visual or object. And finally, we employ a pre-trained fine-tuned sentence pattern textual semantic similarity task to generate the final soft label, the degree of the relatedness between the caption and the visual context. And we adapt 3 soft labels, 0.2, 3, 4. Increasing the threshold beyond this value will imbalance the dataset without any improvement in benchmark. As we can see here in a comparison between the 2 figures, visual classifier confidence and the visual context dataset with the similarity of label, there is changes in the class label, assign the most frequent object in the image when using the caption as a reference by similarity score. And we propose an end-to-end model to estimate the degree of the relatedness between the caption and the visual, as shown in figure A, starting from the generation of the soft label to integration during training. So to leverage the 3 visual information per image, we employ trigram filter CNN on the top of bird embedding. And as we can see in figure B, the model effectively learn word level semantic relation and correlate better with the human reference in blue score. So as the model can effectively learn the visual correlation between the candidate caption and the object in the image, so our first proposed task is a capture re-ranking, visual re-ranking. We evaluate this in 2 models in different sites. And we have benchmark improvement in diversity and blue score for both models. And here's the result with the light model. Just from re-ranking, we have a benchmark improvement across all data sets. Here's some quantitative examples with Vilbert. The model re-rank a more diverse caption, and will Blip, the model select a better candidate caption from the beam search. So the second proposed task is the gender bias evaluation. In most cases, our dataset has more gender neutral, and therefore we introduce gender visual to caption neutral dataset. But overall, the data is similar to Cuckoo gender bias dataset toward men. In addition, when comparing to previous work that employed reduced bias caption dataset, as shown in the table with lower accuracy in red, our fine-tuned model using the proposed dataset shows less negative impact on accuracy benchmark when using the combined visual context with the caption. And here are some results with our best performing model that successfully maintain accuracy in the 5K text test set. By leveraging the visual plus caption semantic relation, our model can estimate the correct gender in image during inference time. And finally, we introduce an application for this dataset, visual context-based image search. The model takes the visual context of the image as the input query and aim to retrieve the most relative image from the database using caption matching. As we can see in the first example with zebra class label, we extract the object from the image and then attempt to retrieve a similar image from the database by matching the caption. The limitation is the system is very sensitive to the false positive label by the classifier, as we can see with the last example with the fountain class label. Here's some results with our best model on the 5K test set using object information, using the KNN brute force similarity search and BERT as a sentence or caption match. To conclude, we have proposed a Cuckoo-based textual visual semantic dataset. The dataset can be used to leverage any text-based tasks such as learning the semantic relation, similarity between visual content and candidate. We also introduced two tasks and application can take a benefit of this dataset. Our dataset and code are publicly available on GitHub and Hugging Face. That's all from my side. Thank you.
Thank you.
Yeah, that's
Okay, so the next talk is at 10:40. So we'll have a coffee break until 10:40, and we'll be back at 10:40 for the talk by Jiajun. Yejo, are you there?
Yes, I'm here.
Okay,
I'm actually speaking exactly the same thing, so to
great.
on-site audiences as well. We're starting our next speaker sharp 10:40 sharp.
Okay, so welcome back, everyone. So it's my pleasure to introduce Dr. Jiajun Wu, who is an assistant professor of computer science at Stanford, affiliated with Stanford AI Lab and Stanford Vision and Learning Lab. So before joining Stanford, he was a visiting faculty at Google Research, and he did his PhD at MIT and undergrad at Tsinghua. His research areas are machine perception, reasoning, and interaction with the physical world, drawing inspiration from human cognition. So today he's going to talk about concept learning. So the floor is yours, and excited for the talk.
Okay, great. Yeah, thanks, Titus, for the invitation, and thanks for the introduction. Very nice to be here. I'm Jiajun. I work on different topics in computer vision, and today I'm going to talk about visual reasoning, but in particular, concept learning across domains and modalities as requested by this workshop, the theme of the workshop. Okay, so concepts are important and humans will use them a lot in different types of seeing understanding tasks. For example, okay, for example, if you look at this picture, then I can ask you questions like, okay, what color is the fire hydrant? And to answer this question, you have to understand, okay, what is mean by color and what is mean by fire hydrant, right? So you have to associate these kind of concepts with and their semantic meanings with the visual input. So in this the answer in this particular case, the answer is yellow. And if you look at a different picture, then I can ask you how many zebras are there, and then you have to tell zebras from giraffes, and then you have to do some kind of reasoning about like counting to give the correct answer, which is 3. So the same, the notion of the concept is important and generalizable because you use it for very different tasks. For example, if I show you, this is a simple picture from the Clever dataset, and clearly there are concepts like colors and shapes and materials. And there's a green cube made of metal, and there's a red sphere made of rubber. And you use them in answering different or solving different tasks. For example, in visual question answering, you can ask what's the shape of a red object, and then sure you have to find a red object, and you have to answer its shape, which is sphere. But you also use it for different tasks, like image capturing. Oh, there's a green cube behind a red sphere, and also you can use it for instance retrieval. For example, if you really understand what is meant by a rubber sphere, then you can find other rubber spheres from the data set, right? You can do smart instance retrieval. So you can see that there's kind of very powerful visual language understanding systems nowadays, especially like very large scale, those kind of foundation models. And they seem to be doing very well on another task, but especially if you want to, connect them to the visual input, then there's still a lot of limitations. If you really, that leads to the controllability and interactive interpretability aspects of these foundation models, right? For example, if you really want to precisely manipulate the image that those models generated, or to ask them to put this thing next to it or in front of it, then they still have troubles dealing with these complicated requests, just particularly because they don't have a I would say explicit understanding of the concepts. And now the question is it possible for us to incorporate these concepts into some smart, multimodal probably intelligent systems? So there are many, many different ways of incorporating it. And one thing we tried as an early attempt, which is very simple, but you can see it has a lot of limitations, is, okay, what if we just do it directly, in a hard-coded way? So you have a question, what is the shape of the red object in this image? And let's say, okay, we just, try to parse the scene. And let's say this image has two objects, and what are they? What are their attributes? And then you also parse the question, the meaning of what's the shape of the red object. If you run semantic parser and tells you, okay, it's trying to find a red object and query its shape. Okay, then you can do a purely symbolic reason. You take this parse question and you execute it on this kind of symbolic scene representations. Here, you don't even need the vision language input. You just need to find the red object and on this representation and answer its shape, which is a sphere. Right. So this work, this kind of very straightforward approach, seemingly, it works pretty well on Clever. It works really well. It's extremely data efficient because we incorporate more structures. If you train it on 1% of data, compare with 1% of training data, then compare with all these other purely neural end-to-end methods that achieves much higher accuracy. And even on 10% of data, it already achieves almost perfect accuracies compared with much better than the other baselines. Okay. But this approach is straightforward and easy to understand, but clearly it has a lot of limitations. And I would say the biggest limitation here is, okay, you have to assume there's a scene, and scene has objects, and objects have explicit attributes. So how could you get these attributes, right? You probably have to annotate them. So you require concept annotations. And to train a language model to parse the sentence into, I would say, semantic programs, then you require the program annotations. And in the simple data sets like Clever, where objects and questions are procedurally generated, this is no problem. But if I want to generate the natural scenes like this, and are there animals grazing, then I ask you, how can you do the scene parsing? Then where are the concept annotations, and where are the program annotations for these kind of, I would say, more general images? That's a big problem, right? I don't have annotations. What is the program or concepts for these general scenes? So now it's 2023. So there's a more than solution, and maybe you have been aware of that. So people say, okay, symbolic stuff are not very popular for a while, but then suddenly there's large models, and they say, okay, but we can actually make these models even better by having some symbolic structure. So methods like Viper GPT, which is very cool, and they have this kind of new idea, but it's really an old idea, but it's modernized, contextualized with these modern models, in the sense that, okay, let's say I don't have annotations of these programs, but I assume Codex has been powerful enough that it has seen all these different types of sequence-to-sequence tasks. So I can just send a question to OpenAI Codex, which produces a program for me. And then instead of worrying what are the concept annotations in the pictures, I just send that parts of the program with the vision input into a large vision language models or smaller vision language models, but combined using or organized using the programs or Python programs produced by these Codex models. And that gives an answer. Clearly, this idea is very interesting and also works pretty well. But here I'd like to introduce a kind of slightly older, but still interesting and novel idea. And possibly, we'll see later that it is not really, I would say, contradictory or incompatible with this kind of approach, but really they can be combined. So it's kind of orthogonal different directions. That is, okay, in the area without large models, and later we can incorporate these large models. We have this interesting idea that is it possible for us, because we don't have concept and program annotations at all, but for natural images, but maybe we can have them, the learning, we can do some joint learning of concepts and semantic parsing. So having the learning of each bootstrap and help the learning of the other. So how concept learning and program learning can really help the other. So let me show you a concrete example about how this is possible. So let's go back to the simple example of there is a red sphere and a green cube. Okay, so what are the concept representations, or what are the concepts that should be learned here? So here, there are objects, which means there are two objects, and every object you probably want to represent it now with some feature vectors, right? Because you don't want to assume I have the space of all the features or attributes I care about is the shape and sphere, shape and colors and materials. So you want to capture the more general appearance of the objects or materials of objects. Therefore, you probably have a concept embedding of the object. So what is this object? And in addition, you parse the language into sentence into semantic form, then you want to filter red and you want to query its shape. But here, instead of assuming, because you no longer assume the space of all possible attributes. So instead of assuming you know what a red is, you probably want to also learn, okay, what does it really mean by red, right? So here again, we're not we're using a preaching model. So everything here is learned just from this data set. So you have no prior knowledge about what an object is like and what red means. But you want to do this kind of joint learning of the concepts and the programs. And eventually everything can be put together into a neurosymbolic reasoning system, which I'll explain later, to output the answer that is sphere. So here the concepts are the visual representations and concept embeddings for the words, and the programs are the semantic forms. So how program learning may really help concept learning. So we have this kind of neurosymbolic concept learning systems. Back then we don't use large models, but now we can later we actually try to incorporate them with large models. But without large models, how this can be done? I have now here I'm showing how program learning may help concept learning. So assume I already have the semantic parsed form, which means, okay, just think about it. Now you can get it by Codex, right? What's the shape of the red object means? I want to first find something that is red, whatever that means, and then I want to query its shape. So having this program, how it can help concept learning, I can execute a program. I can take this object embeddings, and then every program like future or finding red object, it can be implemented and realized as a small neural network, like MLP, but you can now also replace it with, for example, a pre-trained object detection module, whatever that is. I can take this color projection network, which takes the embedding of the objects and output, okay, what is supposed to be embedding of the color of the object. And you can do that for different objects. And then again, there is an embedding for red. So I can compare the embedding of the red with the color of object 1, and they seem pretty different. While the embedding red with object 2 seems pretty close. Therefore, I say there's a high likelihood that object 2 is actually the red object. And then I can now move to the second step to query the shape of object. I can have a module that takes the embedding of object 2, but then now hopefully derive the shape of object, and I can compare that with possible embeddings of different words like cubes and spheres and cylinders. And you find that the shape of the object is very different from a cube, much closer to a sphere, and very different from a cylinder. Therefore, okay, it's very likely that, okay, the shape of the object is therefore a sphere. Okay, so now you can output an answer. This neurosymbolic module can execute it and output an answer that is sphere, but here every module can be made differentiable so that they can be chained together. And finally, you get a very weak, very important supervision, that is whether the answer is correct or not. You can use your output answer produced by these neurosymbolic modules with the ground truth answer to compare the difference between these two answers. use that as a kind of a very weak but important supervision. And again, because every module here is made differentiable, so you can use backpropagation to update the concept embeddings for the objects, but also the concept embeddings for the words. Okay, so this is basically a high-level idea about, again, all these different small modules, right? Again, idea is based in 2019, but now these small modules can be replaced, can be modernized. Semantic parsing can be done by codecs. Whatever project now, MLP can be replaced with object detection networks. But the idea still applies. But there is a chance that we can actually do some kind of joint learning of all the concepts from visual concepts, but also language concepts, and as well as actually learning possibly the language. So this is basically how program may help concept learning. And there's just the other direction is how concept learning may help program learning, which is a bit more involved, and especially because back then the semantic parser we use is not really differentiable, so we have to use like reinforced policy gradient methods, which is a little bit less relevant here. And now, especially if you replace that with foundation models, and the whole story will change. So I'm not going to talk about that in detail, but just I want to give a high-level idea of, okay, these things should and can be possibly done jointly. Okay, so this is kind of a high-level idea behind this work, which we call a neurosymbolic concept learning. And back then, we also have curriculum learning schedule where we start with simpler questions. Oh, what are the object-based questions? What is the shape of the red object? And move to relational questions, like binary questions, right? Is the green cube behind the red sphere? And finally, you go to very complex scenes with many objects and complex questions that requires, longer step or many step reasoning. So this work in neurosymbolic concept learning is really mostly done by student Jiayuan Mao, who's sitting over there, is an MIT PhD student. And she has done a line of very exciting work. This is just one of them. And the advantage of that is we can do, highly accurate reasoning, sort of compare actually better than end-to-end methods. But also, again, it's at the same time, it is equally data efficient. Only on 10% of data, if you train on 10% of data, we achieve almost perfect accuracy on Clever. While again, the baselines like Mac, they can only do 85%. And we can do combinatorial generation, for example, because we now have this kind of disentangled representation about what is the world, what is an object, what are their attributes. So you can train it on objects with, scenes with fewer objects, simpler questions, and where every method can do well. But you can test it, well, simplify setup. I can explain more in detail, but this is simple setup. But during testing, you have scenes with more objects, with more complex questions, and your method have a similar performance, while you don't really suffer from generalization that much. And because we now, instead of assuming we have the library of concepts that are predefined, we're learning everything at the same time. So this thing is directly generalizable to natural images and natural questions. I can actually test it. What is the color of fire hydrant? And I can find a fire hydrant queries color, and the answer is yellow. And I can find the zebras and count them, and the answer is 3. And finally, I can do instance retrievals of finding new horses because I know what a horse is. I have an embedding for it. I can just do a nearest neighbor retrieval and finding all the horses, all the persons. And the thing is compositional, so I can also find compositional concepts like, can you retrieve me of persons on the skateboard? The whole thing is purely discriminative at this moment. So I cannot generate a picture of a person on a skateboard. I can only retrieve, but there's no reason that I couldn't, replace these discriminative networks, which just output embeddings with a generative network, with the hope of in the future, we can combine that with stable diffusion and these kind of things, or also single-sided pictures with compositional structures. Okay. When I keep talking 2020, I can talk about basically what I described in an hour. I can explain every component in detail. But now it's 2023, so I talk about this in 15 minutes to give time to the more exciting, actually equally exciting, but more recent work that from our group, which is a lot of them are actually kind of built on this, I would say, important idea of learning what is a concept and how can we find a representation to capture the meaning of these concepts, but also their different, the grounding and possibly their language in a syntactic form. So we want to, at the core of all these different work is this, you can call it a system, a model, or a representation, that how we can have, which part of a concept can be symbolically represented, which part of a concept has to be neurally learned, And even if something has to be symbolic represented, to what extent, these symbolic representations can be realized in the context of neural network that can be made differentiable. So still allows end-to-end training. Okay, but very quickly, I will show you just a few extensions about how we have applied the idea of learning concepts in very different domains, right? Because this is open domain, whatever reasoning workshop, right? So how we have applied this idea to very different domains. So first we show it, how you can use it for dynamic scenes, and we can go from 2D to 3D. And we can go from 3D dynamic scenes in the sense of human motion. Okay, human move and they have different actions and reason about their actions and learning concepts about their actions. And finally, can we learn action policies for it, right? So if I say pack, I understand what pack is. I can ground it. I can retrieve actions of pack. But most importantly, when you say pack this for me, I understand how to do it, right? So I have this action, the policies have action parameters. So is it possible for us to also learn the policy for the concept so that I can use it for robot manipulation as well? Okay, so very quickly, I'll just show a few slides for each of them. So from static to dynamic scenes is kind of straightforward, but you may not have realized how much information is there in dynamic scenes and how much, how many more new types of reasoning that it supports. In particular, if I show you a picture like this, sorry, a video like this, then you can of course answer descriptive questions like what color is the second, right? Here requires a temporal reasoning that collide with the science cylinder. But you can also do causal reasoning in the sense that I can ask you what objects are responsible for the second collision and what will happen next and what will have happened if the great object is not there, right? So these are kind of different types of reasoning that I can only do on videos. And back then there were no very good data set for it. So we have this data set called Clever collision events for video reasoning and representations, where we have 20,000. You can see that based on the appearance, it's based on Clever, but we generate interesting video events and have 20,000 videos and 300,000 questions for it. So dynamic reasoning requires the understanding of dynamic concepts, right? That's the difference between earlier neurosymbolic concept where everything seems static. But now I have to understand if I want to ask what's going to happen next. You have to, of course, recognize what is a blue sphere and a yellow objects, that's standard. But you have to also understand events or actions like collide. What does it mean by collide? Can I localize? Can I ground collide? And can I retrieve other collisions from the data set? So we have been building systems where you can see it as an extension of the concept learner, which we call dynamic concept learner. So clearly, I don't have time to talk about this in detail, but the high level idea is so simple. That is, everything marked in red is what is added, right? So compared with concept learner, now you have a dynamics predictor. You take these objects, but you have another neural network, which is a graphical network, try to predict how they will move. And on top of that, in addition, you have the visual features like what is an object, what is it by red. You have temporal sequence features and interactive features with the hope of capturing what it means by collision. And you have a semantic parser. This can be done by Codex as well now. And then you have a neurosymbolic executor, which really learns and understands and grounds the words like collisions and movings, but ground them into the visual features of objects that you can answer questions like these dynamic reasoning questions. And similarly, you can use backpropagation to update the embeddings of these features. So what you can do is now the system can ground. You can see that localized objects, but then ground understands what is meant by collision. You can see the bounding boxes and what is by out. The object enters, object leaves, and the object out. And here just a few more examples about what it can do for concept grounding. And you can use that now because you can do concept grounding. Of course, the same system. You can learn what learning concepts can be used for reasoning questions like what is the color of the last object to collide with the metal sphere, and what will happen next, right? Because we have a dynamics predictor, so you can go from what is there. Everything now showing black is the prediction. So I can show this again, where what will happen next. Okay, in this example, I'm showing black is the cylinder and collide with the blue sphere, right? So that's what we have seen. And the cylinder and the red object collide, that's not true, right? That's not happening. So you can correctly answer these predictive questions. And because again, you have this notion of objects, what is an object? Their features. Then this disentangled representation allows you to very naturally and easily extend it for counterfactual reasoning. So if I show you a video like this, but then ask you, okay, without the red sphere, if the red sphere on the top left is not there, then what will have happened, right? So you can do that. You can run the same system, but it's removing the objects And that allows you to simulate what's going to happen. And then you can see, okay, the answer is, okay, is the cylinder going to collide with the blue object? That's not happening, but the yellow object and the cylinder actually has collided, right? So this kind of very straightforward extension from static to dynamic scenes allows you to many more different types of reasoning questions. The 3D scenes as well. Instead of having the input as a 2D image, you can do it for 3D point clouds. And now you have, referring expressions like select the microwave that is close to the kitchen cabinet. You have to understand all these concepts, but now in 3D, what is a microwave? How the shape look like? So you can localize it from the point clouds. What is it by close? By doing 3D, not just like two bowling boxes, but then two objects, which one are closer to each other? So you can do these kind of different types of multi-step reasoning questions in 3D. And the idea is, again, very similar, but this is 2023 work at this CVPR. So we do have codex as a semantic parser instead of a pre-trained semantic parser. I try to align the positions. So you can sort of see that it's very similar work in the sense that now you have 3D object entry encoder for point clouds, but you have the program so you can execute it. So that allows you to, but now with codex help, so it's more powerful and generalizable natural language in particular. So you can localize the target objects. As an example, if I ask you, can you find me facing the couch from the side you're sitting on it? So that's kind of a condition. And then choose the cabinet that is to the right of the couch. Then you have to find the couch, and then you find the cabinet, and then you try to, do some kind of steps of reasoning where you have to answer, okay, which cabinet is really on the right of the couch. And eventually you can localize the cabinet among these multiple different cabinets. And it's not surprising that the thing you can do in 2D, same benefits bring to 3D as well. It is very data efficient on 10% of the data, or actually, sorry, on 1% of the data almost, where you can see that our method already achieves very high performance, while these pretty neural engineering methods require a lot of data for training. And that 1% of data, when 1% of data is available, then they don't do as well. And also generalizing to new scenes, generalizing to new pairs of questions. So it really excels at data efficiency and generalization compared with the other engineering methods. And just like, in 2D, we can do concept retrieval, retrieving other images. In 3D, we can also generate different types of tasks. Here's this example about, okay, the training task is, okay, can we do, 3D visual grounding, referential expression grounding, but I can use it for question answer as well, right? So I can ask you, is there a chair between the table and the windows? And I can ask different types of questions about existence, counting, about objects and the relations. And you can see that our methods is very easily and flexible. We can generalize it to this very different task. Okay. Then of course you can put things together, dynamic and 3D representations. Okay, we chose a specific domain that is human motion, because human seems very popular and these days and getting a lot of attentions, and also it seems to be very useful. So if we can understand complex relations like, okay, what body part does I will show this. What body part does the person use before they kick? Then, okay, the answer is the right hand. And so this seems a nice domain where also can get some data for it. So the method is so similar in the sense that I'm not going to introduce it again, but we did build a data set where people can all use. That is, we build on existing data sets like Babel, but then we have real world human motion sequences and queries on different attributes relating to motor cues and temporal relations so that we can query actions about human motions. Like, I'm not going to read it because it seems complex, but querying actions and also querying the directions of what humans are doing and moving, querying about the body parts of the humans. This is ICML this year as well. Okay, finally, we have shown this, you can do it for robot manipulation. So you go from perception to interaction. So we have, now we can, because these concepts, I would say pack or pick and place or collision is kind of passive. But whenever action involves, action like pack or pick and place, and it's so natural that just give this kind of natural factorization about what an entry level primitive is, because you talk about it. And of course, you want to associate it with the action parameters, the policies that you can execute the actions. Not only seeing what is a pack, but also execute it. So you can learn policies mapping from states and goes to the next actions. but based on these primitives, right? So if I ask you to pack the yellow flower into the brown box, then I have already shown how we can learn what it means by yellow or flower, and what it means by having a brown box. But and also I can even retrieve actions like pack. But here I want to learn the parameters of the pack, so that I can actually manipulate objects or push the green blocks into the blue square. So compare with this, purely pre-training fine-tuning paradigm. We have a text encoder, you have an image encoder, and then you just directly learn control parameters. So here we also have this kind of semantic parsing of the program, which can be get in different ways. But then for these different actions, you can do visual grounding and retrieve objects that are of interest. But finally, you have to learn the control parameters with reinforcement learning so that you can actually execute the actions. So here's a demo of our example of how the pipeline works, where you have instructions and scenes, and then you parse it into the programs. And the grounding module works as before, where you find the hexagon, and then you find the blue objects, and then you also find the box, but then the orange box. And finally, the goal is you have to pack it in. So what is the parameter action path policy so that I can actually move the blue hexagon into the orange box? It is something that's together, but this time with reinforcement learning, so I can learn the policy for pick and place to actually execute it. Similarly, it has all the benefits of a visual reasoning system in the sense that it also facilitates generalization, right? If I train on these examples like pack the yellow flower into a brown box and push the green box into blocks into the blue sphere, then I can do zero-shot generalization because now the language part is disentangled, right? So whatever how you get it, especially if you use these kind of pre-trained foundation models, then I can generalize to a new objects, just as in clipboard, those kind of work, where you can have pack the rain. Even if I've never seen the rain before, it will be able to learn how to pack the rain into a brown box. And compositional generalization in the sense that I can, even if during training, I've only seen yellow flower in packing, while green blocks and blue sphere in the pushing example, I can now push the yellow flower into the blue sphere square. Okay, so this is kind of an example about how flexible and generalizable idea is. Right? Once you have this core notion of concepts and you have the right way of representing it, inferring it, modeling it, then it is the same idea can be very quickly applicable and generalizable into very different domains. And they all have the same benefits of being, data efficient. They perform really well, but then they're very data efficient. Also, they can have very good generalization to new tasks, new environment, and especially on combinatorial generalization. Okay. So now it seems we're in a very good state. We can do 2D reasoning, we can do 3D reasoning, we can do dynamic reasoning, we can do human motion understanding, we can do robot manipulation. So is there anything that is left that is still not being done? Well, all these things, especially the 2D, 3D thing, we show that you can generalize it, you can use it for question answering, you can use it for captioning. But I would say, if you look at these different domains, right, here are examples from these very different domains. Is there a rest sphere to the left of the large sphere? Is there a dresser on the left side of the cabinet? What part do they use or the person use before they move to the left and the person is trying to walk to the left? Or ask the robot to put the T to the left of the Y A. You see that, okay, I would say these domains are so different. And you want to ground them in 2D to 3D to motions to policies. But what is shared is the concept. And in particular, you can see that, okay, here there's the notion of left, right? And when I say left, what appears in your mind? It's kind of this abstract concept, but we sort of understand, okay, what left really means, and we have no problem in grounding them into these very different domains. So there's something that is shared by all these different domains. And before we have been treating them separately, every project here is a different paper and published at different conferences from ICML to ICARE to CVPR. But They really have to be very different domains. They have to be separate projects, have to be separate systems. Also, probably not, because what is really shared, the notion of concept, in particular here, the concept left, has a domain independent form. That is, when I ask you, is there an object to the left of the target, right? You can use LLM or whatever, but what is shared by the question across these different domains? It's the notion of the symbolic form. Okay, what does left really mean, right? Or left means I want to find an object that there exists another object what is on left, whatever that means. Okay, so this notion of left, the symbolic form, is really shared by the concept left across all these different domains. But what is not shared in these different domains? What is not shared is, I would say, the semantic domain-specific grounding, right? In the 2D case, A is left of B means, okay, the bounding box is on the left of B. In 3D, you have to have a notion of, okay, what is the canonical viewpoint and how the point clouds or 3D bounding box are to the left. And in the notion of robotic manipulation, then you have to also associate with different visual appearance and action power parameters of the objects, because if I only move it to the left, then my action policy has to be different, right? So you have very different domain-specific groundings of the concepts of what really left means. But what is really shared is the symbolic form that is after find something which is on the left of another object. So now the question is, and this form is so generic that now the question is it possible? I can write it up, right? I can have this domain independent reasoning of what left is, which possibly produced by LLM. And which means, okay, there is an object that is on the left of another object, target object. And what I really need is to learn from different domains is domain-specific grounding. In the case that, for 2D images, I want to, in the particular question of, is there a red sphere to the left of the large sphere? I want to first find a red sphere. So here, is there a red X and the X object which satisfies both the predicate red and sphere? And on the left of another object, what the other and then here, of course, I also have to find a red object, the other object, which is larger sphere. But then, is there an object that satisfies, okay, both it is being red and sphere, and on the left of the other things? So here the answer is yes, I can find the other objects. And I can have a similar reasoning process, but in a different domain. For 3D, is there a dresser on the left side of the cabinet, right? I can find a cabinet, and I want to see, okay, the dresser that satisfies these predicates, and I can answer this question. I can locate this object. Right. So of course, what is a cabinet or what is a dresser, or even what is left really means in 2D and 3D are different. But on the top, this form of, or the notion of executing, or I would say, yeah, the structure of left and how it can be instrumental in guiding you and finding the specific predicates and their execution is shared. And similarly for motion sequences as well, I can find, okay, is there what the person used before they move to the left? I want to find what left is, and then I can do the reasoning and find the right parts. And in execution, I want to find an object. What is there's a white object, and the object is in the shape of letter A. And I want to find the T, but then T also satisfies the predicate left. So that I can execute it and I can get the control parameters. I can really put object to the left of the letter A. So we really want to find a way that we can unify all these learning of all these different systems, so that we can have one system that works on generally all these different modalities. So very recently we have this new work which is still currently under review. So instead of having a neural symbolic concept learner, we call this logic enhanced foundation models. So we have foundation models, everyone knows what it is now. But how we can incorporate this kind of logic structure, but we introduce them so that it facilitates learning of what a concept left is. And at the same time, we understand in the symbolic form of what it is, but also we simultaneously learn the grounding of left in all these different domains. Right? We just have one system that works for all of them. Now for 2D reasoning, 3D reasoning, temporal sequence reasoning, and robot manipulation. That's a uniform framework unified framework for concept learning and reasoning across different domains and tasks. And it has a domain independent reasoning module, as we said before, about just produce what the form of the left, which is an integration of a foundation model interpreter and a differentiable first order logic executor. And it has domain-specific grounding modules for each different modalities, which has to be learned separately, because as we said before, left means different things in 2D and 3D. So there are parts that are shared across domains. There are parts that are not shared. You have to learn for each domains. And it does have very strong performance across different domains and companion generalization to novel tasks. So this work in particular called What's Left. And in addition to this and many other work I showed before on rule manipulation and human motion reasoning as well, is done by Joyce Yu, who is sitting there as my PhD student at Stanford. Okay. So at a high level, I think I'm out of time. So I'll try to wrap up in 3 minutes. I have until 11:30, right? So
I need to double check the schedule. But
yeah, I think I have 11:30, but I try to wrap up in 5 minutes, but we can have a few minutes in questions. Yeah. Now we have this domain independent system, which is an LM interpreter, which try to output a form of what left is. And then now I have to learn the predicates, right? I have to but this domain form which independent LM interpreter which output the form of left is, and I have a first order logic executor, which again can be made differentiable. So the whole thing can be made differentiable. So remember this old idea I talked about earlier, you can actually do joint learning of these concepts. So instead of using Viper GPT style or visual programming style, which is they have a Persian LM and they just output a form, and then you just take it as is, and then you can say, okay, execute it on whatever the visual input. And every module there is pre-trained. There's no fine-tuning, no learning, it's inference only. But here we don't have to do that. Here we don't have to do that because all these modules can be learned jointly. So it actually allows the joint learning of concepts. So this can actually, you can use it for training. Of course, we don't have that much compute, so we keep the LLM frozen, but there's no reason that you cannot fine tune it as well if you're at Facebook or Google. Okay, and you have different domain specific modules for grounding. For different modalities, you have to extract features for them, so you can use different modality specific feature extraction modules for 2D, 3D, and for graphs. And you can learn relational features. Again, these predicates, they can be unary, what is color, what is yellow, what that means. It can be binary, what is behind, or what is left, right? It can be ternary if you have multiple entities in the predicates. And these domain-specific modules can be unified with this earlier, unified with this earlier module, which is the domain-independent, LM of the form generator and the first order interpreter, so that you can take the embeddings. Now, what is changed across these different domains is the embeddings that you have learned, right? Okay, the embeddings of the vectors here for 2D, for 3D is probably different. But in the execution module, okay, how you can execute this program, or what does it mean by exists or counts? And these things are really shared across different domains. So we have one unified framework, and it really works very well across all these 4 different domains for 2D, 3D, temporal, reasoning, and robot manipulation. You can see that achieves better results on earlier methods, including our own methods, but also state-of-the-art methods like support for robot manipulation. And similarly, it retains all the data efficiency. So compare with especially NQM methods training on 10% of data, and also the first one's in 2D, the second one's in 3D, where you can train on 10%, even 1% of data on 3D, then achieves much better results. And also it can do zero-shot generalization to novel tasks. So here, if you train on Clever, as we said before, you train on these different domains, but then you can generalize to different versions of Clever, because Clever has been so popular that people have come up with different variants of Clever that has different types of reasoning abilities. And it significant outputs from prior methods when you try them to when you try the method and it's on its zero-shot generalization to complex reasoning tasks. Okay, so this is left, and which our attempt to unify our reasoning abilities and learning these neurosymbolic concepts across these very different domains. And in some sense, we have been talking about different modalities. There are 2D, there's 3D, there's human motion, there's robot manipulation. And finally, let me use 1 minute to wrap up by showing sensory modalities can be different things. It can be 2D, 3D input modality, can be language, but it can also be sensory modalities. And in particular, we have been talking about what is an object, what is a sphere, what is rad, its appearance, attributes. But if you really look at these objects, then we have been only focusing on what it is. What is that object? And how, maybe a little bit about how to talk about it, or how to refer to it. Its semantic meanings and connecting it to the words. But especially if we're computer vision people or perception people, then the space is much richer, really multimodal. Here the modal is not input modalities, but sensor modalities. So if you look at object, you not only want to reason about it visually, oh, can you find me the right object? But you also want to really understand its appearance in 3D, how the thing may look like from different viewpoints and the different lighting conditions, how the object may sound, what a sound it may make, how it may feel, which is very relevant in robot manipulation because tactile feedback is so important, and how it behaves. Right? A little bit we have been talking about it in dynamic reasoning. So I just want to do a very quick advertisement of our work on object folder, which we try to build a data set of multi-sensory neural objects, where we try to learn, I would say, this popular neural implicit representation for each object that captures their intrinsic properties about their visual appearance, their acoustic properties, their tactile properties, so you can query it with different viewpoints or with different ways that you may interact with it, so that it will just produce the visual, tactile, and acoustic responses for these objects. Before, we have been doing it only for synthetic objects, so we have 1,000 neural objects in simulation. But we do have implicit representations for each of them, which is unified representations, and you can use it for different tasks in vision and robotics. But just in this year's CVPR, we also try to incorporate it with real objects so that you have this neural representations for not only synthetic objects in simulation, but also real objects, where we try to collect their visual appearance and the sound they will make using impact hammer and microphone arrays, as well as the tactile responses, how they really feels. So this was two purposes. One is to really calibrate our simulation methods to make sure that our simulated visual, tactile, acoustic feedbacks and these neural representations really align very well with their actual responses. And the second is you can do some two robotic experiments. So we have now 100 neural objects, 1,000 neural objects and 100 real objects in this CVPR work called object folder benchmark. We also have defined a number of tasks in recognition, reconstruction, and robot manipulation that people can use by leveraging our multi-modality here, multi-sensor modality systems. Okay, so to summarize, we talked about how we can learn concepts in these very different domains, and is it possible for us to build a unified framework that capture what is really being shared and domain agnostic across these different domains, and what has to be learned for each specific domain, what has to be grounded. And a little bit about the sensor modalities aspects about how we can build assets that really captures the visual, acoustic, and tactile properties of our objects we interact with. So a few things, I guess people always talk about is, in what sense, how much do we need really learning and how much do we need modeling, right? Especially when these foundation models come up and it's like, okay, everything can be learned end to end, right? In many ways that is true, especially if you have data, but the type of data fundamentally is, in some sense, we're fundamentally limited by the type of data we have, right? There's so many images and texts on the web and maybe some videos, but for a lot of things we care about, there's just not that much data. For 3D, there's much less data, especially high quality data. And for human motion, for other things, you just have much fewer data. So in that sense, especially even if you want to have an end-to-end system, you probably want to leverage the data from different modalities, and you want to capture and exploit what is really shared across these modalities that allows, I would say, zero shot or at least few shot generalization to novel tasks, novel environments, and novel modalities, right? So what is really domain independent? What is domain specific? And how can we really facilitate generalization? If otherwise you're capped, you're kind of bounded by the data modalities you have, right? So I think this workshop is very nice because really emphasize the importance of learning across modalities. Otherwise, all you can do is your system has to take either image or text as input or output, or maybe video, because there's a lot of video on the web as well in the future. So hopefully, the system can take image and text and video as input and output image, text, and video as output. But what if you want to, use it for other tasks, for robotic manipulation, for human motion understanding? There's so little data. If you only use the data from that particular modality, you probably won't going to get a very good performance for these tasks. So now you have to leverage data sources where you have a lot, but what is really shared across these different modalities, and if you can capture that, then that will really facilitate the social translation to, I would say, modalities where you have much fewer data for. Thank you.
We'll open up the Q&A. By the way, when you ask what's left, I truly understand it. What's left to be further researched?
Yeah.
Not actually the spatial indication of left.
No,
or are you indicating both actually?
Yeah, that's why we choose this title. Yes,
Okay.
supposed to be a pump.
Thank you for the talk. Okay, so my question is, when you use the generate the code that they, so this kind of code is often kind of fixed. But in reality, a lot of times like there are multiple solutions, right? So we could have like multiple possible code, and then we often also have some kind of dynamic code. So can you comment a bit on?
Right. Okay. So you're essentially saying instead of operating a deterministic program, we should operate a probabilistic program, which makes a lot of sense to me. I think conceptually that is totally true. Ideally, everything here, every code here, it should not be a deterministic program. It should be a probabilistic program because you may have multiple interpretation of it, and even for at a grounding level, the word of the specific grounding of the object can possibly have it's like a probabilistic distribution. That's exactly actually how it was implemented as well. So it's not like purely binary. And here, you can imagine the thing may have multiple different interpretations and which one is really correct. And for the process of finding the right interpretation is also learning is a learning process as well. But even you can do perfect, you have perfect knowledge, you can do your learning has already been done perfectly. There are things that are still ambiguous. So that is a very good point. I think that makes a lot of sense to eventually model that. So far, we haven't been doing that just because I feel like even the deterministic part is not really done that well yet. But I think in the longer term, but there's also a separate issue of, do you really have to have explicit probabilistic distribution, or do you just want something? Now think about it. The GPT stuff you use it is probabilistic, but it doesn't give you a probability of what exactly the sentence it is. So there's a separate question of whether you want a system to be probabilistic or whether you want to actually have that tangent distribution. But in the longer term, yes, if there's a way that we can make the system work better, then we would love to look into it.
I wonder how can you adapt the concept learning strategy in open book study? There's a lot of concepts. I think many people in the field right now just use click embedding, but I think that can be suboptimal because with many workers show that click embedding is not convolutional at all.
Right. So that's exactly what I've been saying, right? Although we have been doing very limited, to that extent, very limited here, but I think it's very promising that the way that we have been doing it, including making these modules differentiable, that actually allows you to do, I would say, end-to-end training backwards. So there's no reason we have not been doing it because we don't have the compute and data. But there's no reason that if you have a system, let me see. I need to find out about this. Cannot. Oh, here. Okay. Right. If you have a system like wrong slide. If you have a system like this, and you have the specific grounding modules at the end, but in the grounding modules, they're all kind of approximated and with embeddings and the domain independent reasoning modules here, the logic executors, they're all made differentiable. Then there's no reason that you couldn't do the things we did in SCL, that is using an answer to update the embeddings of these words. Or eventually, back then in SCL, we don't have large models, but now you have a foundation model, whatever at the top as input, there's no reason you couldn't fine tune it, right? So I think there's hope, especially if any large companies would like to try it, that you can connect these, models, but not using them as a frozen system, but having them output, like putting them into the loop of these bigger systems as we have been doing. But because everything, at least in many different domains, they can be very differentiable in the sense that, it's possible that you can train all these different domains at the same time while updating the embeddings you have been learning by these large models. So it is possible that, your embeddings will just be more effective or more generalizable. CLIP is limited, could be because it was specifically trained for, image capturing. Yes.
Yeah, I really appreciate the mention you were trying to have a unified model for the software. I would say it's actually an old idea, you're modernizing as well. So this is trying to do that.
Sure.
In your domain we use. But what really at the end people would encounter it when you gain the insight from vision domain and abstract all the visual appearances into concept. When applied to dynamics, we sometimes underestimate the complexity of dynamics. And actually dynamics where we have to interview and interact with the system. So for example, in your models, if I recall correctly, you are essentially using linear model to model the motion of the object.
Well, okay. Maybe I have two things to say on that. First, and that is a specific work. That work is actually not part of this. Second, that work, even that work, there's a neural network, it's graphical network. It is not a linear thing.
Yeah, what I'm just trying to say is maybe when we are trying to generalize from a visual concept to the dynamics concept, there's many more.
Right.
For example, just simply thinking about collision, two plus plus.
Right.
There's all kind of thousands kind of ways to pass.
Right.
And leads to all kinds of effects.
Right.
Right.
Yeah. So
we appreciate your insight on
yeah. So
generalize to this
Right.
complicated
Right.
evolving scenarios of
right. Well, I think there's a important notion I have to be aware of. That is, just like for RAD and for the static concepts, like what we're doing, you have at least, so far we have been mostly doing, right? You can take the object, you can classify it, you can say, okay, computer vision, have to take an object, classify as a cat or dog. But here is like you have an embedding of it, and then eventually you say, okay, you compare it with different wording embeddings, you can actually locate, tell the category of the object. So it's a different way of doing it, but it's still a discriminative system. I think that is very important because the part is discriminative in the sense that if you extend it to dynamic scenes, then yes, I think I agree with you that it's much more complex and there's just much harder to define what is collision. But you don't really have to define it because all you need in most cases is a system that can tell if there's a collision going on. So all you need is a discriminative system. Yeah, it's complex where collision may happen this way or that way, or there are different definitions and different domains. But all I need is a system that can tell if there's collision happening or not instead of synthesizing all these different types of conditions. And eventually you may want to do that, especially if you want to do image and video generation, as I sort of suggested before. But you can, of course, start with a two-unit system, which is supposed to be much easier to do. And that's exactly I feel like humans can do. Because if you ask me to imagine 5 collisions, I couldn't do it. But if you show me a video and ask me, is there a collision going on, I can probably say yes.
Yeah, that's the reason why when I asked what's that.
Yeah, that's right. Yeah.
Okay, I think
very nice talk, I have a quick question about what you think is basically, okay, so first started logic and so on were the first line of attack on these problems, right? That people found them to be either inflexible or brittle, or they didn't go to new concept. And now with LLMs, there is a new rejuvenation, neural methods and code generation specifically. And I think that is super exciting, but do you think it tackles the fundamental problems between the folks now?
Well, that is a good point, especially if I want to let personal logic do everything. And I agree with you that it is not, but it could be the case that, we can draw an analogy to human reasoning in the sense that, we can sort of do long horizon reasoning, but we don't do extremely complex. I'm not really, well, it's debatable, but I would say probably it's very unlikely that I'm running very complex logical executions in my mind. But I do some kind of reasoning. If you ask me, oh, is there a rest sphere to the left of the object? I do, first locate the rest sphere and then the large sphere and then see if they're on the left. But there is some kind of logical symbolic executions in mind. And so you're just saying, oh, if I delegate everything to first order logic, that's kind of not really scalable, or that's kind of limited in domains, which is probably true. But if you look at the n-level primitives of what is actually being realized and how these things are being run, then these n-level primitives right now, they're neural networks. And if you look at Viper GPT, they're actually very powerful neural networks. They're like detectors or depth estimation neural modules, right? So depth estimation itself probably cannot be done by first order logic, but that is the neural part that, so you can make leaf nodes much more powerful to address the scalability issue.
Give an example, for example, for this question that you have the left of this is that. Suppose those questions were a bit more complicated with way first order logic questions. The left is not very well defined.
Yeah.
But I think the main challenge is how we combine that with an LLM side by side, where the LLM has to come with some first order primitives that don't exist. It has to be made on the fly.
Right. Well, that is a good point. Well, in the cases where, that sort of connects to the very first question about left, there could be ambiguities and then many different interpretations. There are cases where it is very well defined. It's like here, I can imagine there are cases where left means very subtle things, like, in politics, for example, it's much harder to define. Actually, it's very interesting because even in politics, it draws an analogy. That's why we call it left instead of up. Because there is a relational. You can compare the political positions of the two political figures. So that's very interesting. But let's say there really is a domain that is very hard to define what the meaning is. But in the worst case, you can just delegate it to a VOM. Let's say you can always reduce your entire system to a large VOM by taking the question itself as the leaf node, the root as the leaf node. Right.
Thank you.
Okay, we'll take our time. Let's thank our speaker one more time.
Thank you.
Okay, so our next speaker is Dr. Srinath Sridhar. So Dr. Sridhar is an assistant professor in the Department of Computer Science at Brown University, where he leads the interactive 3D vision and learning lab. And he also spends time at Amazon Robotics. He received his PhD from Max Planck Institute for Informatics and MS from University of Michigan and bachelor's from Anna University in Chennai. So his research focuses on 3D spatiotemporal visual understanding of human interactions. And his research is human-centric, object-centric, and interaction-centric to understand the world from videos and images. So I'm very excited to listen to this next talk that we have from Dr. Sridhar. So the floor is yours.
Thank you, Tejas, for the introduction and for the invitation. I'm just gonna, because this is a multimodal workshop, I have audio as well as video. The slides are a little bit bigger than usual, so I'm gonna try to, PowerPoint is crashing, so I'm gonna try to set that up first. So I need a minute for that.
No problem, yeah.
Okay. Right. Okay, good. I think that works. All right. Thanks for the introduction. And
okay, so sorry, just you need to share your screen on Zoom? So that's.
Oh yeah, sorry. Let me try to do that. I think multimodality is going to probably have a few challenges because we need to share both audio and video. And it's going to get even messier than before. So hopefully this works. Let's see. All right. How about now? Can you see my screen? Okay.
Yes. And we can also hear it very well.
Okay, perfect. Good. All right. So yeah, I think Jiajun's talk was a good segue into some of the stuff that I'm going to be talking about today, which is going to be on multimodality for dynamic 3D understanding. Right. So scenes like this of a person playing a xylophone. How do we capture such scenes? How do we use such scenes, to understand the dynamic 3D world? Not just in terms of vision, but also in terms of the audio, as well as text descriptions of what's happening in this particular audio. And because this is the drum workshop, of course, I had to show drums being played and captured in high fidelity from all three text descriptions, as well as synchronized audio. All right. So, just to motivate this a bit, and before I do that, I'd like to thank all of my students. Much of the work that I'm going to be talking today was led by several of them. All right. So as humans, we lead extraordinarily interactive lives. For example, we may go to a market, pick up, inspect vegetables before we buy them. We may interact with other humans in the market to get more information through speech and natural language so that we can make a decision about what fruits to purchase, what not to purchase. We use large machinery to build infrastructure like bridges, buildings, and we do this through collaboration and communication with other humans. We do household activities. For example, this is an example from the Epic Kitchens data set of peeling a clove of garlic. And you see that there's associated sound with this as well. So we use multimodal sensory inputs in order to be able to interact like this. And we also use our hands to do fine-scale manipulation activities. For example, using our sense of touch to figure out how to woodwork. So these are all things that we do on a daily basis. And it's possible that my PowerPoint has crashed. Apologies for that. Let me try this again. Yeah, my slides have way too many videos, and I think that is not a good idea. Let me try to start this again. And I may have to switch off my video just to save some compute. Let me try this again. Yeah. Hopefully this works. Let's see. All right. Okay. So where were we? Yeah. So if you want to build machines, if you want to build AI systems and robots that can interact with the world just as humans do, not only do we need to look at vision, not only do we need to look at visual sensing, but we also have to look at all the other modalities that include sound, text descriptions, perhaps a sense of touch, and so on and so forth. Right? So we really need a multimodal dynamic 3D understanding. And dynamic because the world is moving, right? So it's not just sufficient to look at static objects and images, but we kind of have to look at dynamic scenes and so on. So today I'm going to be talking about a few projects from our group that addresses the connection between multimodality and 3D perception, as well as multimodality and dynamic 3D perception. So I'm going to be talking about a couple of different projects that cover these aspects of multimodality in 3D understanding. Okay, so first let's start with dynamic text-based 3D shape generation and editing. So consider the following scenario. So let's say you're a designer and your goal is to help someone design a 3D object. So in this case, party A is, wants to design a building. They provide a description of the building and the designer goes off and designs this 3D model, right? And then party A looks at it. They're not quite happy, so they suggest some kind of a change. And the designer redesigns this building. And this process continues until both of them are sufficiently frustrated, and eventually they come to an agreement on what is a good design, right? So this process is highly dynamic, right? Meaning both the party A as well as the designer are in constant communication with each other. And this process is also in 3D because the output that we're looking for is a 3D model of a building or of whatever object that the person is interested in, right? So the design process is really dynamic. It happens over an extended period of time, and it is multimodal because there is 3D shape involved as the output, but the input is actually language description, what the person is really interested in, right? So in order to successfully do something like this, we need to be able to support this kind of recursive text-based shape generation. And of course, we want AI systems to do this instead of the designers. So eventually we want this to be a machine learning system or an AI system. Okay, so let's look at some of the current work. There's been a lot of existing work that tries to cover all of these aspects, right? And I'm not going to go over all of them. There's been some really excellent work, but I will point out that most of the existing work is limited to one forward pass text to shape estimation. They do not typically support recursive generation. And by recursive here, I mean this kind of a dialogue-like process that the users and the designers go through in order to generate these 3D shapes. So that's what I mean by recursive 3D shape generation. So that is not currently supported by many existing methods. So our goal was to do something like this, right? We want to support the generation and editing of 3D shapes where the user would provide an initial description, let's say a chair, and the system would provide a few examples of different kinds of chairs. And these are 3D models of chairs, right? So that's why you see from all these different sides of it. So this is like, standard text to 3D shape. But we want to go a step beyond this, where we want to take these generated shapes and have the capability to add more, add more description to refine this 3D shape that we've just generated. So in this case, it's a chair, but we wanted to have, let's say, separate legs. Right? So this yellow chair that you see here, we render something that has separate legs. So that's like the second step in this recursive process. We can kind of think about this process as being continued, right? So where we now want armrests that can hold your arm, right? In addition to this chair, but which doesn't actually have armrests, and we want to be able to support that as well. And so on and so forth. So we can kind of continue this process in a recursive manner. So this is what I mean by recursive 3D shape generation. Of course, this is a challenging problem for several reasons. First, there are no current existing data sets that can support training machine learning algorithm to support this kind of recursive shape. And second, how do we capture all the fine scale detail that we have in these 3D shapes? Oftentimes, when people refer to changes in 3D shape, they're referring to small details. So how do we capture some of these small details? And then finally, how do we support this recursive editing process, right? Where we start off with an initial set of shapes and we kind of want to recursively edit. So in some work at NeurIPS last year, we presented a solution for some of these challenges, and I'm going to be briefly walking through some of this. I don't have time to go through all of the details. I know that I'm between you and lunch, so I'm going to kind of be a little bit high level on details, but I'm happy to take questions offline. But this was work that was led by my PhD student, Rao. Okay, so let's look at the first challenge, which is the unavailability of data sets that can support this kind of recursive shape generation and editing. So there are existing data sets, for example, the text-to-shape data set that provides annotations for a single 3D shape taken from the ShapeNet data set associated with the text description of what that shape is about, right? So this exists currently. But of course, this is a single shape description here. It doesn't provide like this recursive, we don't have multiple phrases that describe the same 3D shape, right? So what we did was we took this existing text-to-shape data set and we augmented it in such a way that we can support recursivity. And the way that we did this was we take the entire text description that is available in text to shape. We do constituency parsing of the shape description, of the text description. And once we have the constituency parsing and we have the constituents of the language description, we then cluster them across different shapes in the entire data set. So what we get is, for example, if it's a description like a wooden chair, we get all the shapes in the data set that correspond to this wooden attribute. And then we can add more detail to it, right? So if you're interested in only wooden chairs, but also dining chairs, we cluster it in such a way that we get wooden dining chairs, and so on and so forth. So what we essentially get is we go from this reasonably sized text-to-shape data set onto a much larger data set that supports this kind of recursive text editing tasks through constituency parsing. All right, so that's the first challenge. So we've taken an existing data set and augmented it in such a way that it's useful for this recursive shape generation. The second challenge is how do we keep some of the high quality details in the shape? Because oftentimes when people edit shapes, they're referring to these small scale details, right? And here we build upon existing work. Specifically, we use the methods called VQ VAEs. In particular, these are vector quantized shape representation that give us the ability to model the fine detail in 3D shapes. And at a very high level, these representations essentially have a 3D grid where each grid cell has a probabilistic representation of each feature representation of how that local shape should look like. And this can be used to represent not only single shapes, but also categories of shapes, because the grid locations are considered to be probability distribution, so you can actually sample them at inference time to generate different kinds of shapes. So these are the representations that we use in our work. And then finally, how do we actually do the recursive 3D shape generation editing? And for this, we designed a neural network architecture, which we call Shape Crafter. And the idea is as follows. In a classical generative modeling approach, where you want to go from text to 3D shape, you have some kind of a generative model, which takes in text input. It synthesizes a 3D volume. In this case, that is the vector quantized representation that I talked about earlier. And we can then sample this 3D representation in order for us to get different kinds of 3D shapes. Right? So that's like, one thing that we can do in order to go from text to 3D shape. And this is like an unconditional single forward pass generative model. Now, if we want to support recursion, then we need to be able to take in a new text phrase that adds something to the first iteration. So the first iteration was essentially a chair, right? And now what we want is a chair with 4 legs, right? And so what this generative model does is it takes in this new phrase in addition to whatever it had before. It also takes in the feature map that corresponds to the previous time step of that text description. And it combines both of these information to generate a new 3D feature representation, which can again then be sampled in order to generate a chair that has 4 legs. Right? So this is the high-level idea of how this method works. So let's dive into a little bit more details on what this recursive generative model actually has. So the recursive generative model has 3 components. So first, it has a text feature extraction model, which is responsible for taking in text descriptions and creating features that can then be used to synthesize these 3D representations. Right? So that's the idea of the text feature extraction model. And here we just use off-the-shelf BERT for doing this. We use BERT to extract features from text descriptions. We use a linear layer to remap that to a 3D volume, and then the 3D volume is used to synthesize 3D shapes. So that's the text encoding part. We then have residual blocks that are responsible for taking in the feature encoding from the previous time step and making sure that we incorporate information from previous time steps when we do this recursive editing process. And then finally, we have a random transformer that combines both these pieces of information, the previous time steps shape representation, as well as the text description, in order to synthesize new shapes that are representative of this recursive editing process. Okay, so how does this look like? So here's a few examples of this recursive editing process. There's a lot going on here, so I'm going to highlight the most important bits. So first, for example, in the chair category, we can see that we can start off with an initial shape. We don't support color for now. So what you see here is only the shape part of it. So we start off with an initial chair representation. And we'd like to edit this in such a way that it conforms to a certain description. So in this case, we'd eventually like to make this chair more circular. And it appears to be some kind of a competitive chair. I don't know what competitive here means, but at least it's circular for sure. Right? So Shapecrafter supports this kind of recursive editing process where we start with an initial shape description and kind of fine tune it to make it more circular. We can also support global modification of shape. So we can start off with a chair that has slats in the back and make it look more like a comfortable chair with the cushions and so on and so forth. Right? Same thing for tables. We can also support part level modifications. So we can change things like, have the table have 4 feet instead of just one pedestal, right? So we can do things like that using Shapecrafter. And then finally, we also see out of distribution generalization to some extent. For example, the data set does not have any table that has this kind of an L shape, but we were able to kind of synthesize these kinds of L shape without any additional supervision. So we see some degree of out of distribution generalization. All right, so what I described so far is just the first kind of method that we built on for this approach. There are of course some limitations. One of them being the trade-off between quality, especially fine details, and how much text description we want to take into account from the previous time step to the current time. So there's always a trade-off. At CVPR this year, we address one of those limitations. So for example, we are interested in capturing really fine scale details in object shapes. And this paper, which was a collaboration with folks at Autodesk, proposes a classifier-free guidance approach in order to extract more details for text to 3D shape modeling. This does not support recursive shape generation, but this can still be used for capturing more quality. And if you're interested, you should drop by the poster on Thursday at 10:30. All right, so let's see how much time I have. Okay, I still have half an hour. That gives me plenty of time to talk about the second piece of work. And again, I'm going to try to keep it 20 minutes, and then so that there's also lunch break. So I'm sure. All right. So the first thing that I talked about is essentially a text to 3D shape generation method, which is also recursive, and therefore it's multimodal, right? So we are seeing how these foundation models like BERT and perhaps CLIP can be used to ground this with 3D shape generation editing, right? And that's really useful for many downstream tasks. The second thing that I'm really excited about is some recent work from my lab where we're interested in dynamic multimodal 3D understanding. So we want to be able to look at dynamic scenes, understand both the shape as well as the appearance of dynamic scenes in full 3D, so that we can do lots of more interesting things that involve motion as well as 3D. So I'm going to talk about a new data set that we've been working on for a while now, and I'm going to show some interesting results. All right. So neural fields are representations that are becoming more and more common in computer vision. We've seen an explosion of work in neural fields in recent years. The classical example being neural radiance fields or NERF, which has shown how to capture high quality shape and appearance using just posed 2D images, right? And we've also seen advances in using neural fields to represent 3D shapes, for example, DeepSDF. And there's been hundreds and hundreds of papers in the last couple of years that use neural fields in various different ways for representing shape, appearance, as well as other modalities. However, these neural fields still lag behind classical representations in some ways when it comes to how we use them. I mean, for example, in 2D, pixels are kind of the standard representation. And they've been developed for decades, and we can watch YouTube videos of hours and hours with synchronized audio without any problem, right? So we can all go to YouTube and stream videos with audio, right? And similarly, there are lots of excellent techniques for processing 3D data like meshes, and there are tools that allow us to modify these meshes very effectively. We don't have any of these capabilities, or at least not readily available with neural field representation. So if we were to model the shape or videos as neural fields, you don't have very good tools that allow you to do these kinds of things, right? And there's two reasons why we cannot do this. I mean, one is obviously the algorithmic advances, right? These pixels and 3D meshes have been around for a very long time, and therefore there's been a lot of algorithmic advances. But neural fields are, relatively speaking, newer, and therefore we don't have as many advances, although a lot of people are working on this, right? And the second reason is because we don't have very good data sets that allow us to advance these algorithms. And therefore, that makes it harder for us to easily address these kinds of problems. Okay, so what we wanted to do was we wanted to kind of look at what's out there, when it comes to the data set aspect. So the rest of the talk is going to be more on the data set aspect than on the algorithmic aspect of enabling these neural fields. So we kind of took a look at what's out there in terms of existing data sets that support this kind of neural field advances. And obviously, there's been a lot of great work in trying to create data sets for neural fields research. For example, if you look at just generally scenes, right? So there's been a lot of work that proposed data sets for building NERF models of scenes. And one of the advantages with NERF is that we've kind of gone away from using synthetic data onto the real world, because NERF allows us to very quickly go from posed images to 3D representations, right? So that's been really helpful. So many of these data sets are real world data sets. But what we are missing, though, is none of these data sets have other modalities. For example, text descriptions, that's something that's lacking currently in existing data sets. And also, these are usually handheld smartphone videos captured around objects. So we don't have like a 360-degree view of what's going on in each of these data sets. And furthermore, they obviously they obviously lack other modalities as well. For example, audio is something that's missing from most of these data. There's also object-centric data sets, for example, ShapeNet, as well as OmniObject 3D, which is a paper here at CVPR. You should definitely check it out, as well as the stuff that Jiajun talked about on Object Folder, which support object-centric reasoning, object-centric learning. And some of these data sets do have things like text descriptions and sometimes even audio. So Object Folder, for instance, has audio data as well. So you should definitely check out these two papers at CVPR, which are quite relevant. However, both of these data sets and other data sets lack dynamic 3D scenes. So they don't have like a dynamic, 3D objects, objects that move, objects that make noise as they move, and so on. So that's still lacking. And of course, there's hybrid data sets as well, such as Core 3D, Perception, and so on. So there's these kinds of data sets, and again, these data sets lack these kinds of text descriptions or audio descriptions. So what we wanted to do was address some of these limitations with existing data sets. So we wanted to build a data set that's 300 and that provides like 360-degree views of objects, of dynamic objects that make sound or some kind of noise that we can record. And then finally, we wanted to have detailed text descriptions of what these dynamic objects were actually doing. So that was our goal. And this is work that we call DIVA 360. DIVA stands for Dynamic Visual Audio Data Set. And this was work that was led by a large team of students, but particularly led by Chengyu, Payson, and Angela and Michael. All right, so what is DIVA 360? So let's talk about DIVA 360. So DIVA 360 stands for the Dynamic Visual Audio Dataset. And this is a data set where we put objects in a table-sized capture system. And we have cameras on all 360 degrees. And I'm going to show you how this capture system looks like. So we have cameras on all sides of this object. We also have microphones that record from 6 different directions. So we have directional microphones all around the space as well. And what we do is we capture both dynamic scenes. So in this case, we have a dynamic data set that captures different kinds of activities, like the activity that I showed earlier in my first slide, where a person was playing a musical instrument. You have data sets like this. Also subtle interactions, like a person assembling an object or screwing in a screw and so on and so forth. We also have a static data set, which is more object-centric, right? So this is objects that don't move, but we still have a very large collection of these objects, and we provide annotations for this. So what are the advantages of this data set? So first of all, this is 360 degrees view. This has detailed text descriptions for all the scenes that you see here. We also have objects with 6 degree of freedom pose, so we know exactly how the pose of these objects are. And then we also have spatial audio that records dynamic scenes with rich audio. All right, so let's look at some statistics of this data set. So we have 2 data sets, the dynamic and the static. We have 46 dynamic sequences, which range from 5 seconds to about 3 minutes long. We have 1,360 seconds of synchronized video and audio from 54 different directional cameras. In total, this is about 8.6 million image frames. For the static data set, we have 95 static objects across 11 categories. For all objects, we have pose annotations. We also have 30 multi-object scenes. So it's not just single objects, but also multiple objects in the same capture environment. And in total, for both these data sets, we have over 8,600 words of text description that describe either the activity that's going on in the scene or the object that is in the scene. So this is the DIVA 360 data set. Okay, so there's a few challenges in building a data set such as this. The first challenge is we need to have a camera capture system that can record all this sensor information, synchronize all this sensor information, calibrate them together, as well as we need benchmarking metrics and that can support different kinds of tasks on top of this data set. So that's kind of the challenges here. So I'll talk about briefly about the capture system. So what we've managed to do is we managed to build a table scale capture system. So this is like this box that you see here. It's about the height of a person. And this box has roughly a 1 meter cube capture volume. And this capture volume contains lights. It contains 54 cameras, 6 microphones. And here you can see an interior view of this capture system. Right? So we have all these different lights here. We have cameras. The black dots that you see here are cameras. And we also calibrate all of this. There's also 6 microphones all around. This is also a light stage, so we can actually make the data in there look like it's from different scenes. Okay, so again, to recap, this is a table scale scene. We developed our own custom hardware as well as software in order to support synchronized, high resolution, high frame rate capture of both video as well as audio. We have our own software for calibrating the lights as well as the cameras. And then we also have manually labeled text descriptions for dynamic scenes as well as the static object. Okay, so how does this data look like? So again, this has audio, so I'm going to try to increase my volume here, and let's see if that works. So here you can see 46 of the 53 different camera views. These cameras are capturing at high definition. They're capturing both video and audio at 120 frames per second. And here's an example of a toy. We labeled this as wolf, but somebody pointed to me that this toy has a name. Bluey, yes. Okay, it's called Bluey. So maybe we should change the name of the data set. But anyway, so we have toys that make a lot of noise, but we also have hand interactions, very subtle hand interactions. And if you listen carefully, you'll hear the noise of the screw being screwed. Or did I? Yeah, let me play that again. Yeah, so here you can actually see the fruits being put into the bowl. So why do we care about such subtle sounds? So there's actually a lot of evidence from cognitive psychology that multimodality and especially sound matters a lot. I'm going to pause this here. And the reason is because if we look at how our visual cortex and our motor cortex is wired, in monkeys in particular, it turns out that when we perform a manipulation activity, there are some parts of the motor cortex that light up. The same parts light up when we observe somebody else performing a manipulation activity. And what I found really interesting was that 15% of those neurons light up when just hearing a sound of that activity being performed, right? Which I think is really fascinating. And that points out to the fact that there is a very strong correlation between vision and the audio that we make while we perform activities, as well as text descriptions of what's going on. Right? So that's the reason why we care about some of these subtle sounds. All right, so let's see. We also have the static data set. Of course, there's no moving pictures here, but essentially we capture about 95 different static objects across 11 categories. We provide pose annotations for this, so you know exactly what the orientation of these objects are. This is similar to ShapeNet, which also has aligned poses for all of these different objects. So this is really useful for doing object-centric reasoning. And in order to obtain the 3D pose of different objects, of course, it's very hard to manually label for the 3D pose of objects. So we actually built a self-supervised method that can actually label the 3D poses of objects using no supervision whatsoever, no human supervision whatsoever. And the method that we use for this is self-supervised canonicalization. And this is going to be a paper at CVPR. It's a highlight paper tomorrow, so you should check it out if you're interested. But the idea here is, let's say we have a bunch of neural radiance fields representing objects from certain categories. So in this case, cars and chairs. We've built a method that can canonicalize these neural fields, or in other words, align these neural fields in such a way that all these cars face in the same direction. So we try to align the 3D pose of all of these objects. And you should definitely check out this paper if this is interesting. And we use this particular method on this data set so that we can obtain the poses across all these 11 categories and 95 different objects. Right? So we did not manually label for these poses. Okay, and this was work that was led by Rohit, who's also at the conference, so you should talk to him if you're interested. All right, so data is only useful as far as you can propose tasks on it, and you can propose benchmarking metrics that can support these kinds of different tasks. So for the dynamic data, we actually propose metrics as well as evaluate different methods of these benchmarking metrics. So we kind of at the first instance we are looking at reconstruction as the metric, and here we use standardized metrics from the neural radiance field community, the peak signal to noise ratio, the learned perceptual similarity, and so on and so forth. And we evaluated 2 methods for evaluating dynamic scenes. For static scenes, again, we use the same metrics as reconstruction before, but in addition, we also have a post-canonicalization metric that tells us how good the alignment of these different shapes are. And we evaluate different methods on this metric as well. So I'm going to show some examples of the dynamic scenes and what we can do with such dynamic scenes. So in this case, we have dynamic videos of the that I showed earlier, and we're interested in building dynamic nerve reconstruction of these scenes. So we want a reconstruction of both the shape as well as for appearance. So here you can see some of the results. And this is, this is in full 3D. You can see the normals here, and of course, this is the results that you're seeing here are from a per frame instant NGP. So we're actually fitting for every frame in the video sequence. We are fitting an instant NGP model, and we're able to create these kinds of dynamic 3D scenes by fitting it on a per frame basis. So in addition to all the annotations that I mentioned earlier, this dataset also has foreground background segmentation masks, that can be used to do such reconstruction. And here you can see an example of this fine scale manipulation activity that I talked about earlier. And this also has synchronized audio, so you can kind of hear what's going on in this dynamic scene as well. All right, so just to point out a few things here, one thing that we found surprising in our experiments is that there are techniques like mixed voxels, for instance, is a technique specifically designed for dynamic, nerve reconstruction, and per frame instant NGP is fit on a per frame basis. One thing that we found surprising was that a per frame instant NGP actually works better than these methods designed for dynamic 3D reconstruction. And oftentimes it's also faster than these methods. So I think that's something that we hope that future methods can kind of build upon. We also don't, our goal is not to saturate these metrics, right? So we still want to keep room for others to kind of improve upon. So the numbers that you see here are not the best numbers, but at the same time, that's not meant to be the goal here. We want others to kind of improve these numbers. All right, so we do the same thing for static data sets as well. So here you can see an example of, the car category. We provide like a 3D reconstruction and 3D representation of cars, chairs, and a bunch of other things as well. I'm going to skip through this, but we also provide metrics here and for different categories, as well as we compare different methods across the pose estimation metrics as well. I will show this another example here. So we also have multi-object scenes. These are miniature models of different kinds of objects, right? So we have multi-object scenes where we have tables and chairs, for instance, and we capture them under different settings. So we capture them under a messy setting where everything is disorganized, and in a clean setting where everything is neatly organized. So this can be used for research and object rearrangement and so on and so forth. So we provide 30 such scenes as well. Okay, so just a quick recap. We proposed this DIVA 360 dataset, which is a multimodal dynamic 3D dataset. Right? So we have 53 views of dynamic objects captured at a high resolution, high frame rate, along with audio information. We also provide text descriptions for each of these scenes. So it's multimodal and can be used for a lot of multimodal research. Of course, this work also has some limitations. Firstly, the focus here is not on going to the real world, and focus is not on scaling this to a lot of different objects and a lot of different categories. Right? The focus is still more in a lab setting, where we're focusing on certain specific categories and specific number of objects. The benchmarking metrics that we have currently are limited to vision. We don't have any benchmarking metrics for language or audio, and that's something that we are really interested in doing as future work. And then finally, this is not yet open world, right? So what we want to do is to be able to do something like this, but in the open world. And I think that's still something that is yet it remains to be seen how we can do that. All right. So to summarize my talk, I presented some work on text to 3D shape synthesis, and this was not just text phrase to 3D shape, but it was more of a recursive process, where you start with an initial shape and you recursively edit and generate new shapes as you progress. So that was the first thing. And again, this speaks to the dynamic nature of multimodal data, right? So multimodality is not just about static things, but also about things that move across time. Secondly, I talked about the usefulness of building your own hardware. I personally feel like in vision we don't build as much camera hardware, sensor hardware as we should. And I think for multimodality, this is probably going to be really important because we often need different modalities that are synchronized with each other and so on and so forth. So I think there's still a lot of work to be done. And we've taken one small step in this direction by building this table scale capture system that has the synchronized cameras as well as audio and so on and so forth. And then finally, what our work does not address is this open world understanding problem, which is the topic of this workshop. And I think open domain is still quite difficult. But I do believe that there are some takeaways from what we've done, which is building hardware to capture rich data. For example, this is taken from the Epic Kitchens data set, being able to build such in the wild data that contains all these different modalities, not just vision, but also audio, as well as allowing 3D reconstruction of what we are seeing in the environment. It's going to be quite important for us to scale this up from being in a lab setting to a more open world, open domain setting. So I think there's still a lot of work that needs to be done that I'm excited about. Okay, so in fact, there's actually a very cool workshop, Epic, which is also happening today. Check it out for some more details on this. I'd highly recommend that. All right, with that, I'm going to thank you all for listening, and I'm happy to take any questions. Okay, we'll open up for the floor.
Yeah, I'll ask a very
Yeah.
Just a short question.
Yeah.
When you are building the control system, I saw you put all the calibration parts.
Yeah.
Some of the calibration tables is not perfect basics.
Yeah.
Is it causing?
It doesn't matter because we use the QR codes as feature extractors. We don't actually detect the QR codes. We detect it, get points, key points, and then we use call map on top of that. So it doesn't really matter if the QR code, it doesn't. And also I should point out that that's an older version. Those are removable now. So the QR codes don't stay there forever.
And I have some two questions. The first one is, what do you do with that? It looks like the bottom is transparent.
It is, yes. I didn't get a chance to, yeah.
The bottom view.
Yeah, so the capture volume that we have has a transparent shell that allows the cameras that are in the bottom part of the capture system to still have a clear view of what the object, including the bottom side of the object. So we use a transparent shell in order to achieve that. Yeah, great question. So yeah, reflections are challenging there. So we actually provide the data set as is with the reflections, but we also develop techniques to avoid those reflections, including using. You can model the reflections as well. So it's because you can model the entire light field. You have all these different cameras, so you can model the reflection if you know where the glass shelf is. So that's also something that you can do.
Okay, another question about the dynamic rendering. So basically, you said you can see the NGP to every frame.
Mm-hmm.
That is maybe because you have a lot of views in the hardware. But many dynamic rendering they really work on one camera. The camera is moving, the thing is moving, and so then for that comparison, you use all the views also for the other dynamic rendering method.
No, we actually held out 6 cameras just for validation. That is not used during training. So we have 6 held out views for validation. So that's all the metrics are computed on those 6 held out views. But the greater point which you're bringing up is, what if you don't have those views, right?
Yeah.
You can actually simulate, because we provide this 360 degrees views. You can simulate camera paths inside this volume to create new data sets that kind of don't have that kind of information, right? So I think that's something that we can potentially think about. Thank you. Yeah, I should mention that this data set is not yet public. I'm excited to share it with you. It'll probably be it's a lot of data, terabytes and terabytes of data, so it'll probably take us a while before we can make it public. But I'm happy to take any questions.
I just sent the Bluey video to my daughter. All right, so I think let's thank the speaker one more time. Thank you. And we have also exciting schedule in the afternoon as well. By the way, sorry to compress the launch time for every one of you guys. Our afternoon session will start from 1. Time to start. Teachers, please.
Okay, yeah, sure. Okay, so welcome back everyone to the afternoon session of ODRUM. I'm very excited to introduce Dr. Lane Soor, who is currently a young investigator at Allen Institute for AI, where she works with the Mosaic team. And pretty soon, I think next semester, she'll join UC Berkeley as an assistant professor. She received her PhD in computer science from Cornell Tech and bachelor's and a minor in linguistics from The Ohio State University. Her research spans NLP and computer vision, building systems that use language to interact with people, and designing models and data sets that address problems in language grounding. So over to you, Elaine. Looking forward to the talk.
Great, thank you. Yeah, so today I'm going to talk about two different approaches that I think we can categorize our existing work in language grounding in terms of evaluation. And I want to motivate that we move more towards the second approach rather than the first, and I'll talk a bit what I mean by that later. And so I'm not going to talk about systems. I'm mostly going to talk about what is language and how do we evaluate the systems that are using language. This work was all done at Cornell. Currently I'm at AI2. I'm not really working on language and vision stuff. But in the future, I'll join Berkeley in like 2 weeks, and I will again return to language and vision work. Okay, so I want to contrast two approaches to how we're evaluating our language using systems. And the first approach is what I broadly call this like true conditional semantics approach. And I think we can cast most vision and language problems like VQA and captioning under this general framework. The sort of key feature of this framework is that we have static data, like an image or a video, paired with some kind of text data, like a caption or a question. And essentially what we're doing is a matching problem. So truth conditional semantics here is actually coming from like semantics in linguistics, where we take, under this sort of paradigm, we say that the meaning of an utterance is the set of worlds in which it is true. So the problem of grounding in this paradigm is, given some world W, we want our system to tell us whether an utterance is true or false about that world W, i.e. is it in this set of meanings M, or is it outside that meaning? So today I'm going to look at a particular case study of this. This is going to look at some older data that I've put together that came out like in 2017, where we really focus in on the truth conditional semantics aspect of language grounding. In this case, our worlds are images. But again, you can consider like videos as your worlds as well. And basically the task here is just to determine whether a sentence is true or false about an image. And I think we can categorize tasks like VQA under the same approach, where maybe in VQA, we have a sort of infilling problem where we need to find the best word that answers a question such that the question paired with the answer is true about the image. But this sort of approach is pretty insufficient for covering all different kinds of language use. So how would we pair an image with some kind of imperative or an interjection or a conditional statement that someone's going to act on when you're looking at the image? And what about like dialogue, for example? So this, I think I'm going back to your introduction earlier today, but I believe that language grounding is much more complex than simple image text alignment. And that's basically what I'm arguing in this talk. Okay, so the second approach, which is what I think we should be moving towards, and I think we are moving towards as a community, is looking at language meaning as language use. And so this is also coming from like a sort of linguistics-y perspective from the field of like pragmatics, where we take the meaning of an utterance to be its use in an interaction, its function in an interaction. So there's a few assumptions we're making here. The first is that when we produce utterances, we're doing it because we have some intent that we want to carry out. So when we look at data that's sort of scraped from the web, we can take all that data as a generated from whoever posted an image and wrote the caption, and then they have some intent underlying it. And so in this framework, we have a speaker, right? The person who writes a caption or writes an instruction, but then we also have the audience of that. So for example, in an instruction following setting, if I'm given an utterance, I need to act in response to that utterance. And so one way we can look at what meaning it means here is it is the sort of effect that the action of speaking has on the world. by having the speaker sort of recruit the listener into some kind of action. And this is super broad. So like, maybe I just want to teach you something. So I'm showing you a diagram with some captioning explaining it. And my goal, my intent is to teach you something new. Or maybe I'm giving you an instruction and I really want you to move around in the world and execute something for me. So here we can look at two different uses of language in like how we're looking at grounding. So the first is we can look at grounded language generation, where we, like me as a speaker, I have some world state W, which is like my sort of observations of the world. And I also have some goal state W prime. And I want to generate an utterance that will maximize the likelihood of that goal state being reached by me recruiting my my audience. So this could, for example, an instruction following be me write the best instruction that my listener will execute so that we solve the task together. In language understanding, grounded language understanding requires getting some world, having access to some world state and some utterance that I'm listening to. I want to recover the goal state that my speaker used to generate their utterance, and then I need to act to reach it. And this is assuming that I want to cooperate with my speaker. And when I'm talking about worlds here, it's also super broad. I'm not just focusing in on images. This could include any sort of embodied scenario, even like the real world. So today I'm going to also focus on a case study of how we can study language use, language meaning as language use, which is this environment called Serial Bar, which focuses in on instructions as a form of language use. And again, here we're going to study two different tasks, language generation and language understanding in the form of instructions. Finally, I want to highlight something that we really only get when we start looking at language meaning as language use. And it's the dynamics that arise through language use. So unlike in this sort of static image text matching, truth conditional semantics approach, thinking of language as a phenomenon and an action that we take in interaction allows us to study two really key aspects of language that have not really been very studied as much in NLP or in language and vision work, which is first, language change over time through use. So if I'm constantly interacting with my robot agent or something, maybe over time we're forming a shared vocabulary because over time we are continuing to reinforce one another's language use. But then there's also a second aspect, which is language acquisition through use in interaction, where as I'm consistently interacting with the system, maybe again, we're building some kind of shared vocabulary or a set of abstractions that allow the system to more easily understand me. And so at the end of my talk, I'm going to talk a bit about how we can use Serial Bar to specifically study the second question of language acquisition through interaction. Okay, so today I'm going to sort of divide this into these two different frameworks. I'm going to briefly talk about this truth conditional semantics approach, and I'm going to highlight some of the ways that we can very specifically target in our crowdsourcing procedure, different aspects that the truth conditional semantics approach really is actually very beneficial for. And then I'm going to move on to talk about Serial Bar and meaning as language use. Okay, so first I'm going to talk about this truth conditional semantics approach and highlight again this case study of these two corpora, which are called the natural language for visual reasoning corpora, NLVR. So again, our goal here is to evaluate our system's ability to ground language. And here what that means is, does our system accurately predict whether a sentence is true or false about an image? Now, if we wanted to do as systematic of an evaluation as we could, we would enumerate all possible utterances and all possible worlds. We would get the system to predict for us, and then we would ask the person, is this right or is this wrong? Now, I mean, this is not feasible, of course, because we're not going to be able to run inference on all of these examples. We're not going to be able to get human judgments on all of these examples. And even defining the space of possible worlds and utterances is pretty hard to do, right? Now, there is one benefit of this kind of evaluation of true or false, which is that unlike something like image captioning or visual question answering, it's very easy to evaluate because you just have like this binary, is it true or is it false? But we do have this drawback of we would like to be able to systematically evaluate our models. Can we still do this even though this is actually in practice impossible? And yes, we can. So some of the benefits that we get from testing systematically like this are we are going to be able to avoid spurious biases that result from having only a sample of utterances and worlds paired together. So if you recall some of the earlier drawbacks of some vision and language work where, for example, you could solve a question without actually looking at the image it's paired with. These are the kind of things we'd like to avoid. And if we did have all worlds paired with all utterances, we would not have this spurious bias present in our data set. Unless, of course, our utterance is like tautologically true or false. It also allows us to measure the consistency of a system's understanding of a particular utterance. So let's say we have some utterance and we have the set of worlds that the system predicts it's true for, and then the set of the worlds that the human predicts it's true for. This gives us a really rich set of information about what is our system doing when it's processing language, when it's grounding language. So in practice, what we do when we're creating these data sets is that we want to actually pair utterances with more than one world, more than one image. In particular, we want both positive and negative examples of that sentence's meaning. So in these particular corpora, we focused on a particular set of language phenomena, which is like spatial relations, attributes, compositionality, groupings of objects, etc. But this kind of focus on that particular kind of language is a bit orthogonal to this question of how are we doing the evaluation, and we're doing like this truth conditional semantics approach instead. So we also want to focus, again, what we want out of these corpora is diverse language phenomena. And I'm going to talk a bit about how we actually get this particular feature of our language, but in practice, like I'm going to focus on the general setup. So just to be very brief, we get data like this. So the top one is this data set from 2017. So we have this sentence, there are exactly 3 squares not touching any edge. And this is true, you can see, because in the left box, there's 1 black square not touching the edge. In the right, there's the blue one. And in the middle, you can see there's 2 black squares. And one of them, the one on the top, there's like a little gap between the very top of the image and the square. So that also counts as 3 squares. And so we have a true sentence. For the bottom one, we have real photographs, and we have the sentence, all dogs are corgis with upright ears, and one image contains at least twice as many real corgis as the other image. This is also true. We have 2 corgis on the right, 2 on the left, but one of them is fake. It's a stuffed corgi. So this is true for this image. So I'm just briefly going to go through how we're actually collecting this data. I'm probably going to skip over a few things. There's a few different parts to collecting any data set, especially like a multimodal data set like this one. So the first is we need some images, we need some worlds to write sentences about. We want complex and interesting images, so different kinds of objects with diverse properties. We want different spatial relations, a number of objects in each image rather than just a single object. And our solution is, first, we will generate images synthetically, and then second, for the real images case, we're going to do some search query heuristics. When we are actually collecting sentences, we want sentences that are paired with multiple contexts. This is, again, really important for being able to systematically evaluate our systems as much as we can. So we want multiple images paired with each sentence, and we want both true and false examples of worlds. And the way that we do this is via a contrastive sentence writing task. And I'll show an example of what that means in a minute. And then finally, and this is really critical to collecting any data set, we want to make sure that the data we get is actually matching what humans are doing when they're processing language. So we also have a validation stage where we ask other workers, given an image and a sentence that a worker wrote, whether that sentence is true or false about the image. So sort of going back and asking someone else to do this language understanding task. And this is going to be giving us the gold standard sentence meanings. Okay, so I'm going to go through what this pipeline looks like for this first data set, which is NLBR. So first we generate some images. We basically just randomly place some shapes on this little pattern, or like this framework, or the empty canvas. We designed this so that it is like kind of compositional. So we have different boxes that objects can appear in. We have different configurations of the objects. We will randomly generate a second image, and then we generate 2 more by taking the objects from the first 2 images and placing them again in the bottom 2 images. And this is actually going to be really important for our next task, which is the sentence writing task. So we show a worker all 4 of these images, ask them to write a sentence that's true about the first 2, but false about the bottom 2. So we might get a sentence like, there's a box with 3 items of all 3 different colors. And what ends up happening here is we actually have 4 examples. We have one image paired with a sentence, another image paired with a sentence, and then we have two more, although these are with the false label. So the reason we do this contrastive sentence writing task is the sentences that they write need to be general enough so that they're true for two images. So they can't like enumerate all the objects in each box, but it can't be so general that it describes all of the images, because otherwise the bottom two, it would also be true for. And we do this shuffling process where we take the top objects and put them in the bottom to avoid these trivial descriptions like there is a blue square, because any object in the top two is going to be present in the bottom two. During the validation stage, again, this is relatively simple. We basically show someone a sentence and an image and ask them whether it's true or false. We shuffle the boxes here as well because we want their sentence to be invariant to those like light gray boxes. So we have the sentence, there's a box of 3 items of all 3 different colors. Do we have any guesses of whether this is true or false? Okay. So this is actually kind of an interesting example because I think it's actually more ambiguous than I thought originally. So the annotation here is false because I'm assuming it's because there's not a box that has exactly 3 items where they have the 3 different colors. But this is actually, as an aside, a very interesting use of language because technically the one in the middle does have 3 objects with 3 different colors. It just has more than 3 objects with 3 different colors. So that's like a scalar implicature that might arise in real human language use. It's very cool. So I'm going to even more briefly go through this second version of the dataset, NLVR2, which uses real photographs. We can't generate photographs. I'm actually curious if diffusion models can generate as complex of images as we got from this process. At the time, of course, these models did not exist. So we're going to use image search engines and similarity tools so that we get those like sets of stimuli to get the really interesting language. So we base this off of ImageNet. We find synsets that give us more interesting images, like a lot of acorns will appear together in an image. We will generate and execute search queries to refine it so that we have like multiple objects in each image. So 2 acorns, we use the similarity tools to find like images that have similar color palettes and similar settings and stuff like that. This is just using Google image search. And then we remove low quality images like ones that don't actually contain the synset. And most of this is being done using crowdsourcing. And then we will create a set of 8 images by prioritizing the ones that workers think are interesting. And we will randomly pair them into 4 pairs of images. And this is what's going to be the stimuli for our sentence writing task. So we will ask workers to select 2 of the pairs and then write a sentence that's true about the ones they selected, but false about the other ones. So here the worker selected the 2 pairs on the right and said 1 image shows exactly 2 brown acorns in back-to-back caps on green foliage. Then again, we do the validation task where we show another worker this pair of images plus the sentence and ask them whether it's true or false. Does anyone have a guess on this one? I think it's less ambiguous. Guess you can thumbs up if it's true or false, or thumbs down if it's false. True. Okay. Yes, I think this is true. Yes, it is true. Okay. Yeah. Okay, so I'm just going to very briefly go through some of the data we got from this process for NLVR, well, actually for both of them. So we looked at some of the like linguistic phenomena that we got people to write in these data collection processes. So like one of the things we were interested in was numerical expressions. So we had like exact counts, which we refer to as hard cardinality, like there are 2 and only 2 people. But we also have like bounds or ranges on counts, which we call soft cardinality, like there are at least 2 yellow squares not touching any edge. We also have coordination, like do you have to have 2 properties to be true about the image? There is a box with a yellow item and 3 black items. Negation, like a mitten is being worn in one image and mittens are not being worn in the other image, as well as things like comparisons, like are there different colors of balloons, and universal quantifiers, like both images show a silver pail being used as a flower vase. And one thing I'm not actually highlighting here that I think has been talked about a little bit earlier in this workshop is facial relations. And they definitely show up in these data sets. I just didn't have an example in these slides. That's something that I think I still think is super critical, especially given the talks that we've seen already. And I'm really interested in exploring that further. Okay, so this is NLVR, and this is like the example of really applying this truth conditional semantics approach to building a language and vision data set. I also want to highlight some other work from EMNLP 2021, which is a data set called Marvel that is basically applying a very similar data collection setup to the one I just described, but focusing on a wide variety of languages and different cultural concepts. It's a very cool data set. I think it won best papers. You should all definitely check it out. Okay, so now let's move on to talk about language meaning as language use in an interaction. And again, our perspective here is that every utterance is generated from some context in which it was produced and the intent of the speaker. So I'm going to sort of define this in like a more formal way so that we can then move on to talk about a particular example of what this interaction might look like. So in this collaborative interaction setting, we have two agents that are acting in a shared world towards a common goal, and they will coordinate their actions by using natural language. So this setting exposes two core natural language grounding problems, which I'm going to formulate as different functions that we want to learn. So the first is language understanding, where when we're doing grounded language understanding, we want to map an utterance that we hear, our current world state, maybe what's happened so far in the interaction to some actions. And maybe those actions happen immediately. Maybe they happen, 5 minutes in the future after I've observed my agent doing my speaker doing something else. The second task is language generation. So what grounded language generation looks like is we have some goal and we have our current world state and maybe the interaction's history. And we want to generate an utterance that will most likely reach the goal by having our listener act. So one unique aspect of this sort of collaborative and dynamic setting is the dynamicy of interactions. And one example of this is dynamic delegation, where as the agents are interacting with one another, they might modify their behavior to best support the interaction going forward. So for example, let's say I, as the user, say, can you take the pliers? My system just runs away to the corner of the room. Obviously, that's not what I wanted it to do, but it's not that bad because basically I can just do it myself, maybe issue a simpler instruction that I know the agent will actually take care of. So this is just one example of adaptation that occurs in these interactions that supports language change and continual learning of language. So continual learning and language change is actually very core to how we use and change language. We use explicit and implicit feedback to drive our own language learning. So, when I'm giving a talk, I'm looking at how people, maybe they look confused or maybe they're nodding along, and that gives me feedback on what I should say next. Maybe I should clarify my point, for example. People also expect that the people they're talking to will adapt their language use via feedback. So like if I'm having a conversation with someone and I don't quite understand what my friend said, maybe I'll ask them to clarify or like say, what do you mean? And then maybe they were mispronouncing a word or something like that. But there's all sorts of the little cues that we use in interactions with one another that support these phenomena of language change and language learning over time. And if we build systems that can transform these feedback cues into learning signals, for example, things like facial expressions or head nods or timing, or even the content of what my interlocutor is saying, these systems will both better support collaboration and also they'll learn a lot more efficiently because they'll be making the most of the information that they're actually getting from the interaction. So some kinds of feedback that we might get through these human agent interactions include explicit feedback. So this is similar probably to the more recent stuff on like RLHF, where we're getting like binary feedback from our language users. So we have maybe a user who says, hold this for a second. And my system comes over and grabs the pliers, which is great. So I give it some positive feedback. But then it decides to just run away to the corner of the room again with the pliers. And now I'm going to give it some negative feedback. Maybe this is explicitly like me saying good, good, bad, bad, or maybe it's just my facial expression or some kind of body language, or maybe it's the fact that I run over to it and grab the pliers from it once it starts running away. We also have different kinds of implicit feedback. And one example of this allows us to learn to generate language. So if our system has an intent, like it wants the user to bring it a hammer, but it erroneously generates an utterance or an instruction, bring me a saw, What our user will do, because they want to be cooperative, is they'll bring a saw to the agent, right? And from this, the system can actually derive multiple different learning signals. First of all, it can derive a signal that basically maps, is a negative example of the intent paired with this utterance. It did not verbalize this intent correctly. But it can also have a positive learning signal here, where we have the utterance and what the user actually did. And this gives us a positive example of how our user was interpreting the utterance that it generated. So to just summarize the setting of language meaning as language use in interaction, we have these two agents. They're acting in a shared world towards this common goal, and they use language to coordinate. We can study grounded language generation and understanding. We have these nice dynamic aspects that support continual learning through both explicit and implicit feedback. So I'm going to instantiate this scenario in an environment called Serial Bar, which is a situated and collaborative language environment that with sequential natural language instruction. So this environment is this 3D game environment. We have two agents. They're acting in a shared world. They're surrounded by a variety of things that they can refer to. Like we have a house, we have a windmill, we have some plants and trees and stuff. There's different kinds of terrain that they have to navigate. So they can walk on the grass or the path, but they have to avoid, or they can't walk on the pond or the mountain. So this is not just a problem of understanding language. You also have to understand how to navigate your environment, which is a very critical point of any multimodal work, is you have to understand the modalities very intimately. And then there's also a variety of cards on the board with different colors and shapes. So the two agents participating in this interaction are a leader and a follower. The leader is responsible for doing the high-level planning, a goal creation towards their shared goal. They're responsible for choosing who should do what towards that goal. They're responsible for executing their part of the goal, but then also they need to write an instruction that verbalizes what the follower should do. And they have to write it in this box below, send it to the follower, and then the follower's goal is, or their job is just to follow the instructions as accurately as possible by moving around the environment. So their high-level goal is to pick up matching sets of cards, where you have 3 cards that have a unique color, shape, and count. And this is loosely inspired by the rules of the card game set, if you're familiar with that. So in this particular board, let's see if we can find an example of a set. So I'm going to start off with this 2 pink stripe card. That's by me, the leader. So I'm going to get that first. A second card that might work, that's closer to the follower, is this 3 red triangle card. And then we need one more card that has one object that's not red or pink or triangles or stripes. And one of them that would work, that's near the follower, is this orange square card. This makes a valid set. So if we were to pick this set up, we would earn a point. And at the end of our interaction, we would have a score, which is going to be a reflection of how well did we collaborate. And crucially, how well did we collaborate by using language? So again, language here is sort of the glue that is binding together this collaboration. And in order to do well, we have to use language. We have to expose language's meaning through use. So we designed multiple mechanisms that further encourage collaboration in this interaction. So first of all, we have an observability gap. So the leader can see this full board, but the follower can only see a first-person view. First of all, this is going to encourage the follower to follow instructions as accurately as possible, because if they go off and do their own thing, they're at best just going to waste some moves because they have a limited number of moves. And at worst, they're going to completely sabotage the leader's plan. And because they're working collaboratively, there's no reason for them to do that. But it also requires the leader to write instructions that are actually followable in the environment. So like if I want my follower to get this 3 red triangle card, I can't just say, get the 3 red triangle card, because as you can see, the follower doesn't actually see that card right now. So I'm going to have to tell it to turn around. And again, this is an example of how I'm generating an utterance that when I recruit my listener to act, they will have the best chance of accomplishing my goal. We also have a capability gap where the follower can move farther per turn than the leader. So they're taking turns. And this really encourages the leader to make use of their follower as a partner. It's going to be impossible for the leader by themselves to earn a point, well, maybe 1 point, but probably not more than that. So they really need to recruit the follower towards their goal of picking up sets of cards. So this really encourages the leaders to write instructions that are very high quality and also delegate more complex and longer paths to the follower through their instructions. So let's take a really quick look at what it's actually like to play this game and interact with these agents. I'm going to, let's see. Okay, so I'm going to, oh no, okay. Give me 1 second. I need my presenter notes. Okay. All right. So this should look familiar. This is the same game board that we had before. Okay. Yeah. All right. So as the leader here, I'm going to pick up this 2 pink stripe card first. This is kind of hard to do. So I'm picking up the 2 pink stripe card, and then I want to write 2 instructions to my follower for the 2 cards I want it to get. Turn around and get the red triangles next to the mountain, and then I want it to get the orange card. Okay. So the follower is a neural network model that will move around the environment. You can see it starting to move now, following my first instruction. So it's turning around. It's going past the mountain. We have a bit of a spatial relation here. And now it's selected my 3 red triangles card, which is great. And I just told it to, oh no, okay. So I told it to select an orange card, but there was actually an orange card hidden in this little like valley of this mountain that I didn't see as a leader, which is not great. So you can see here that this is now an invalid set because we have, I believe this was a triangle card and this is also a triangle card. So that's why they're outlined in red. Now that's not great, but actually we're in a live interaction. So all I need to do is like just fix this problem by issuing more instructions. So now my goal is to get the follower to deselect this orange card and reselect the other orange card. Okay, so I'm going to say deselect card you are standing on, and then turn left and get the orange square past the windmill. Okay, so I'm going to end my turn again and let my follower move. Hopefully we can recover from this. And we do. Okay, we've deselected the orange triangle card. And now my follower seems to be going around the windmill towards this orange square card that I needed. And we've got our first set. Cool. All right. So that is an example of serial bar, and it's also an example of one of the models that we trained. And I'm going to talk about how we actually train this model through human agent collaboration, through interaction from live human feedback next. But first, so this environment is an instantiation of this broader collaborative language setting where we're studying language meaning as language use. We have these 2 agents, a leader and a follower. They're acting in this shared world towards their common goal of picking up sets of cards, and they use natural language instructions to coordinate. So again, we can build agents that generate instructions and ones that understand instructions by moving around. We have this nice aspect of dynamic delegation. You saw that I did that because I made a mistake. So I corrected myself and asked my model to do something else. And we have opportunities for continual learning. So the rest of this talk, I'm going to focus on talking about how we can use explicit feedback that people provide in these interactions to improve a model's instruction following ability. And we also have opportunities for implicit feedback. For example, as the leader, I learned I probably shouldn't be so vague in the instructions I write because my follower might pick up a card that I didn't intend. Okay, so now let's talk about continual learning and how this paradigm of looking at language grounding supports this kind of research, more naturalistic language research. So our goal is to learn and improve a system's language use through interactions with human users. And I'm going to talk about 2 ways that we can get feedback from our users to support this. The first is explicit feedback that we use for instruction following. And the second is implicit feedback that we use for instruction generation. And actually, I think I'm going to switch the orders of that. Okay, so the learning overview for both of these works is we're going to initialize our model, our instruction following or instruction generating model. using some supervised data from a corpus of human-human interactions. And then we'll apply supervised training. Basically, it's just behavior cloning to get our model to either generate or follow instructions. And then we put it into the wild and ask it to interact with a human. We don't ask it, but we deploy it in interactions with a human. And in these interactions, we sample actions, which is either instructions or actual like movements conditioned on the state of the world so far. So that's either what's going on in the world, like the current environment, what all's on the board, the first person view perspective, the instruction that the user wrote, if it's an instruction following model. It'll like do its thing in the world by either moving or generating an instruction. We will get our user to respond either by following instruction or continuing to write another instruction. And so we get ourselves some training data, aggregate it into a training data set, apply some contextual bandit training to update the model parameters, and then just do this over and over in a series of rounds. Okay, so again, we're going to look at two different kinds of feedback here. The first is learning to generate instructions with implicit feedback, and the second is learning to follow instructions with explicit feedback. So this first one was presented in Tackle in 2021. This was led by a member of my lab at Cornell, Noriki Kojima. The task here is we want to generate instructions for human followers. So we want to map a world state and some goal state to an utterance that will then be sent to a human instruction follower in this game. The main metric that we care about here is whether the user actually did what we intended. So essentially, how well did the human follower execute this intended action to reach this goal state? Again, this is a measurement of language use, right? There are other metrics that we've used here. So like we can say, okay, well, if our human did this path and the intended path was this one, how different are those? We have some game score at the end. We get some quiz-like feedback from our users after each instruction. The actual learning signal we use here is based off of the task completion metric. So because our agent is conditioned on some heuristically generated goal, we will then compare that to whether our user did what the agent wanted, and this will allow us to construct a training data set. So across 14 rounds of human agent interaction with this learning signal, and this is, again, we have no demonstrations of human instructions being written. We just have this implicit feedback of, did the user do what the system's intent was? And we get a task completion improvement from about 45 to 79% accuracy. This is the number or the proportion of instructions generated by the agent where the user actually did what was intended. So again, the model is continually improving its ability to convey its intent in the instructions that it generates. And when I talk about the model's intent here, I don't mean to say that the model like has some intent inside of it. This intent is actually heuristically generated based off of the game rules. It's just sort of conveying that heuristically generated intent through language. And then more recently, we have a paper from late 2022 where we're learning to follow instructions through feedback that humans provide in live interactions. So the agent's task here is to map a world state W and a user's instruction U to actions that will result in some kind of intended world state. And as our agent is acting in the world, we ask our workers who are just observing the model to give binary feedback. So we have different buttons in the interface and on the keyboard that they can press that will basically send positive and negative feedbacks, and we align those to the actions that the model is taking. So it's a pretty easy way for users to give feedback. They don't have to like look at post hoc each instruction and give some accuracy judgment for the learning process. But we actually do find that these post hoc instruction evaluation metrics are actually important for learning or for evaluating our model. So we do end up sampling some instructions that our users wrote and asking workers after all these experiments whether the model did what the user asked. But when we're actually learning, we're just taking these online binary signals and applying them in basically we have a contextual bandit setting. So we run 11 rounds of training and deployment of our learning setting with about 200, probably an average of 300 interactions per round. On the top left, I'm showing the instruction execution accuracy. And this is again computed post hoc after we've done all the experiments and we've sampled some instructions and showed them to other people and asked them if the model followed the instruction or not. But we see that this rate is continually increasing from 67 to 82% accuracy. Now, one confounder here, actually, before I do that, I'll say, we also see improvements in this very, very high level goal of getting better at the game. So in terms of the game score, which is the number of sets that the two pick up together, we see significant improvements from 3.3 to 5.3 sets over time. Okay, so there's actually a confounder in this experiment, because the population of workers that we're working with here are continually exposed to this model's behavior, right? And we as humans are extremely adaptive in the language that we use. So as they're working with the system across like 2 weeks of experiments, they're going to change the language they use so that they get higher scores, right? So there's a question of whether this improvement we're seeing here is because the model's getting better, or because people are just writing instructions that a like not so great model is actually better at following. So what we do to evaluate this is we take the very first model and its set of parameters and deploy it at the end of this experiment alongside the final model. And this will give us basically a head-to-head comparison of these two models, where one was trained on additional human agent data and the other one was not, but the types of instructions that users are giving are about the same. And we see that there is improvement here. So the model goes from like 67 to 70% accuracy. And when we do analysis, we do see that people change the language they're using when they're working with this agent, but a vast majority of these improvements are due to the fact that this model was trained on additional human agent interaction data. Okay, so I just went through 2 different perspectives on how we should be evaluating language grounding and trying to motivate moving from this sort of truth conditional semantics approach, where we have static data and we're basically doing image text matching, to a more embodied setting of how is language being used in context and in interaction. Okay, great. So I also want to thank a lot of many of my collaborators who worked on these projects with me, and I'm happy to take any questions.
So we are opening up for Q&A. Please.
So these ideas which you were mentioning at the end, which are specific to language, or you couch in the context of language, so things like explicit feedback and implicit feedback, to what extent do they work in things when the instruction, things you try to instruct and not necessarily discrete, say for example, you have a strike and golf ball, some other sort of more continuous ability of implementation?
Yeah, that's a great question. I mean, I think that we should look at how people would naturally give feedback in this sort of setting and try to map that down onto some learning signals. So like, I mean, for the golf ball example, maybe it's like, how many tries does it take to actually successfully hit the ball, or how far does it go? I mean, that's like an example where I don't know if you need language, right? But like, I agree that it's not just a discrete, like this is good or this is bad, it's all relative. Another interesting point is that there's prior work showing that even these sort of binary evaluations of model performance are very context dependent on the user's expectations of the model. So the more I expect from my model, I'm sort of like going to change the range of my feedback based off of how well I think it's going to do. So if I think it's good, I'm probably going to give a lot more negative feedback than if I already had bad expectations of it, even if it's the exact same model. So I think that's sort of like, that's also an example of where the gradation arises, that it's not like hard to explain. Yeah. But I don't think it has to be binary. Yeah.
Thanks for your presentation. It's very responsive. And my concern is about the agents. So the agents work with the environments, like the spatial layout of the environment, and then for the instruction of language.
Is it what? Sorry.
With the understanding of the spatial environments, it's necessary for agents to understand for the instruction.
Yeah, in general, definitely. So in this work, we did take like a slight shortcut, and we actually allow the model access directly to like each location's properties, at least within like a certain range around it, like the first person view essentially. But in general, yeah, I think that this is a broader point for all of these multimodal settings where our perception of the different modalities is very deeply entwined with like our other perceptions. So like the way that we might think about the world and the actions that we're taking in it might be conditioned on the language that we might use in those environments. And we have this sort of bootstrapping process by which like we can only learn to understand our environment if we have words for it, or if we have these like causal relationships with like acting in the world. So I think it's a super important. Yeah. Here the model would know. I mean, it doesn't know. It knows generally like, okay, in this position, that's this far away from me. This is what's in this card. But we also restrict it. Yeah. So it doesn't have to do like direct computer vision, like, you know, pixel level reasoning.
My second question is about the general evaluation. So this is actually a simulated environment, which I had to cut down the real world environment.
No, I have not yet. But I think that this could be really interesting. I mean, I think it's harder when you're working in like an actual physical environment, like with a robot, because you might need a lot more trials and such. But actually, we found that generally these kind of learning signals can be like pretty efficient. So I think it would be definitely interesting to explore in the future. Yeah.
Thank you.
Or at least a more realistic environment like Thor, for example. Yeah.
Exactly, you can generate different simulated.
Yeah. Yeah. I mean, we didn't experiment with that, but that would be definitely the next steps. Yeah.
I have a quick question regarding the maximum of VR business VR too. I noticed that you mentioned about discarding the low quality images, but from a computer vision perspective, first of all, what is your criteria to define low quality images?
Yeah.
And then a follow-up concern is, will that basically introduce bias into the data?
Yeah. I mean, definitely. So the way we defined it was, I think, no clip art or illustrations or something. So they should be photographs. They should contain the object that is being described in the synset. And like inappropriate images we were filtering out as well. Maybe there was like one other thing. I'm not so sure. So in general, yeah, I mean, this kind of process will definitely bias the data set. I think the even bigger source of bias here is that we're using Google Images at all, because we all know that like Google Images is very biased, and there's numerous reasons for this. In general, like, you know, this is all sort of conditioned on the images that people choose to post publicly and the captions they pair them with, which is already going to be, I mean, that's already a really interesting question of like, what is happening there? And I think that's another thing I want to explore in the future is like, okay, we have these images, someone put them here, someone gave them this caption, like, what was it that inspired them to do that? What was that intent? And I think there's some work looking at this from like, I just saw a talk at AI2 from Elisa Kreis. It was very, very cool. Like captions versus alt text versus like the intent that people have and like generating multimodal data.
I have a final question. I think we have time for one more. So yeah, my question was when describing the NLVR data set, you spoke about exploring maybe if you can generate those images using stable diffusion or you know, any text to image model. So like in my experience, text to image models actually struggle with things like counting and spatial reasoning and things like that. So instead, do you think it might be interesting to use NLVR or NLVR like data sets to evaluate diffusion models?
Yeah, that's a really interesting point. I hadn't thought about it from that perspective of like using it as evaluation. Not exactly sure how you do that, but it's a good question. I've thought about it from the perspective of like, given an image, given a caption that would appear in NLVR2, can you generate an image that like reflects the caption accurately? I've tried this like off and on and it violates a lot of these like compositionality constraints. And I think, you know, there's papers coming out every day that are like talking about this same problem. I think it's a huge problem that I'd like to look at more for sure.
Awesome.
Thank you. Now we'll move on to our very
Cool.
Tejas, whenever you are ready, please go ahead.
Yes, sure. Okay. Okay, so our final speaker is Dr. Angel Chang. She's an assistant professor at Simon Fraser University. Prior to that, she was a visiting research scientist at Facebook AI Research and a research scientist at Eloquent Labs, working on dialogue. Angel received her PhD from Stanford, and her research focuses on connecting language to 3D representations of scenes and grounding language for embodied agents. So she's interested in semantics of shapes and scenes and also acquisition of common sense knowledge and reasoning. So I'm very excited to hear the next talk. Over to you. I think you'll have to unmute. Yeah.
Okay.
Yeah.
Can everybody hear me?
Yes, but we can't see your slides actually.
Oh, that's okay because I haven't started them yet.
Okay, cool.
Okay, can everybody hear me and see my slides?
Yes.
Okay, great. Thank you so much for having me and thank you all for coming. Today I'm gonna talk about, I don't know if there's any reasoning, but eventually it'd be nice if there was reasoning with language in 3D. So first of all, I wanted to say a few words about what I work on. So I work on language, connecting language to 3D representations of the world. And in order to basically enable this to happen, I also work on having curating large scale data sets of interactive environments. And all of this is in the hopes of that eventually one day we can develop helpful AI assistants that can talk to us in language and maybe help us around the house. Okay, so here's just a brief list of things that I'm very excited about. I think we live in a very exciting age where there's new work and new publications almost every day. And usually I would, some of these interests probably shared by you. So here, today I'm gonna mainly talk about grounded language understanding, but I think it's also very interesting to have, open world vocabulary for 3D vision problems such as detection. And I'm also interested in fine-grained classification as well as content generation using text. But let me start by talking a little bit about what you can do with language in 3D environments. In some ways, many of these, I think with the exception of the last, is things that you could do with 2D as well. You can localize objects, describe them, and do some form of question and answering. Here, I'll do a brief description of some projects in these areas, and then I'm going to come back and focus a bit more on this line of work about localizing objects in 3D. So this was several years ago, I think maybe 3 to 4 years ago, we had this work. This is in collaboration with Matthias Nissner, and the main student is Dave from TUM, and where we were interested in taking these 3D representations of things. This is a 3D point cloud, and given a sentence such as a black chair in the corner, it is next to a table, trying to identify which object it refers to. And this involves both detecting the objects and disambiguating between them. You can also take the same problem, the same kind of setting, and turn it around and do it in the reverse, where you have the 3D point cloud. And now what you're interested in is identifying the objects in the thing again, but now instead of saying, given a description what object it refers to, you try to say, okay, for each object, let's try to have a description that distinguishes this object and allows the listener to figure out what you're talking about. And we can also take these two pieces of work and connect them in a combined work where we have an architecture that can do both captioning and do this localization, or sometimes people call it visual grounding. And this I'll talk a little bit about as well. But based on these works, we also have community benchmarks and follow-up work. We don't have follow-up work. Others have follow-up work that basically investigates different algorithms and methods for doing both of these tasks. We also run a workshop, language for 3D scenes. It has been going since for a couple of years. We'll have our third iteration at ICCB this year, if you're interested. And then I also mentioned you could also, if given a 3D environment, so here is another visualization of a 3D environment with point cloud, you could also do visual question answering, where your input is this point cloud, and in addition, questions such as how many chairs are there, and the answer should be 8. And this is in some ways a direct analog of 2D VQA, except in 3D, you potentially have more context and more information. For instance, in 2D, especially in single view 2D, where you're given one image, you may be limited in your field of view, and maybe you only see 2 chairs out of these 8. So the idea with 3D is that potentially it's more complete. Another area that I involved with is embodied AI. There's actually an embodied AI workshop today. And in embodied AI, what we have is we have an agent that goes about. This is, I think, in some ways similar to some of the work that Ling has described, but you have an agent, it's in your environment, you can take actions, and the actions that you take will actually have an impact on the environment. The state of the environment will change. And based on your interactions, it will then, what you see could be different, or the state of the world could be different. A simple example of this would be visual language navigation, where you would, given an instruction, exit the bedroom, turn left down the hall and stop in the kitchen, you would want to follow the set of instructions. And one of my students, Sonia, has done some work in this where we have a very simple idea, which is that, okay, usually a lot of the way these models are trained that potentially they want to follow the shortest path. And here we just supervise the actions based on the path that matches the instruction, not the shortest path. So this is a brief overview of some different problems you can do with 3D and language. And here, this one, maybe I'll talk about a bit more in the end, but more recently, we've gone beyond just navigating these environments, but being able to actually manipulate. So here the idea is that you will have a robot and you would want the robot to move some objects, say a toy animal, from some starting place, we call it a receptacle, say a chair, to a target table. And this is just an example of this robot in action. It will want to go to find the stuffed animal, be able to actually manipulate and pick up the animal, and then go back to the sofa and then place it. So this is a new RIPS challenge that we're currently running. You can go to the website. This is a collaboration with Meta and Georgia Tech, and there's basically a big, huge team is involved. I'm just here representing them. Yeah, but you can check out the challenge. And this is on the Habitat platform. But going back to the main focus topic I want to focus my talk on today, it's really about localizing objects. And so this is the scan refer line of work. And here, what we do is we start by creating a little data set of paired text and 3D descriptions. So we start with scans from ScanNet, and we take 700 or so unique scenes from ScanNet, and we ask crowd workers to annotate these. So what we would do is, instead of connecting a description for the whole scene, we would actually collect description for each object in the scene. And the objects were previously annotated as part of the ScanNet project. So we know what these objects are, and for each object we collect descriptions. And here are some examples where it would be a dark blue couch in the center of the room, and this would be a long bar table behind stools. And through this process, for the 700 scenes, we would, and about 10,000 or so objects, we collect approximately 5 descriptions per object. This gives us about 50,000 descriptions in total. And this is just an example of what the data looks like. And why do we, again, I'm gonna reiterate this because it's also an interesting thing to think about. Why do we care about 3D versus 2D? Here's just an example of, we have this description. This is a black office chair. It's against the wall facing the round table, and we want to figure out which one it is. And there are, I mentioned already, some advantages of 3D. Here we can potentially integrate information from multiple views, and we can potentially talk about these long-range spatial relations, which are not limited to a single view. For instance, if we want to say the chair that's furthest from the door, maybe with one image, you couldn't tell which that is. In addition, the other thing that you get in 3D is you get real-world sizes, and this you also have real-world and objects, 3D objects in the 3D are kind of naturally separated by space. But in working in 3D, there are also some challenges. For instance, often we would use egocentric spatial relationships, such as chair to the left of the table. These are inherently view-centric. It relies on knowing from what point of view the speaker is looking at the scene. And in addition, the scans that we're working with are they're reconstructions. So, and it may suffer from reconstruction quality issues. For instance, small objects could just be a blob, and you can't really do much with that. But still, I think having such a data set allows for interesting questions, and you can then investigate what kind of different representations and models do we need. For instance, 2D, when will 2D features work, and how much knowing 3D information helps. So you can then, with this data set, you can then do this kind of potentially systematic investigation. And for much of my work, we actually use a fairly simple 2-stage pipeline, and you could be a bit more advanced, but I think this pipeline is fairly easy to understand. Where given an input scene, the first step is that basically you do a 3D object detector, and you detect what are the objects in the scene. And then what we do is we take the language as additional input for disambiguity and discriminating which object is being referred to. And this is, I think, a very intuitive pipeline. You could, of course, also do something that's one stage, or you can actually, in the second stage, potentially do additional refinement of the bounding box as well. You don't have to be stuck with the initial detections. So there's a different variant. But for the purposes of this talk, I will have this, we will use this two-stage pipeline. And so to go into a little bit more detail in this pipeline, what happens after you detect the object is that for each of the object that you have identified, you can then extract features for them. And often these features will also include not just the features of the object in isolation, but some features of the objects around it and it's where it is in the scene as well. And for the text, for right now, we'll just say, okay, you use some magic encoder where you will take the text and then you will transform it into some kind of latent space, a vector representation, and you will do something. And then from that, we can then somehow fuse the two modalities, the text and the 3D features, and then we add a MLP on top to determine what object is it. So this is the pipeline. And once you have this pipeline, then you can, of course, there's a lot of details about the different components and what design choices you make for each. For instance, starting at the 3D representation level, you can, there's different ways to encode the scene. A popular choice nowadays is with point cloud, but you could also do voxels, you could do some kind of you could also include other kind of information, like multi-view information. And for now, we'll start with point clouds. But even here with the point clouds, there are choices of what kind of features, input features, this is before it has gone through your deep neural network, what kind of input features do you have? Your typical choice is to have the position, maybe potentially the normal associated with each point. And people have also found instead of using the color directly, it's a bit more, the model performs better if you use what's called multi-view features. And these are features that you would accumulate for each point by rendering different views of it and then associating with that point. In addition, people also do data augmentation. And this really helps because we are limited in the amount of 3D data we have. So typical data augmentation will be kind of maybe jittering the position of the points a bit, potentially rotating about up, and then maybe some flips about the horizontal axis or, yeah. For the 3D object detector, again, we can have design choices there as well. You can have a good oracle choice would be to use the ground truth, see how well you perform, then that allows you to decouple a little bit of how good is your object detector versus how good is the rest of your system. And two popular choices for the 3D object, actual 3D object detector, real detectors would be either VoteNet or point group. Both of these are works that are based on using PointNet, which basically takes points and then passes them through MLP and then, associate features with them. I'm not going to go into detail about either VoteNet or point group, but let's just say sufficient to say that different 3D object detector. Maybe I say one thing about point group versus VoteNet. Point group is actually, so VoteNet is actually 3D object detector in the sense it finds the bounding box, while point group is more of an instance segmentation network, from which once you have the instance segmentation, you can then obtain a bounding box. Again, these features, then for the features, often these features that are used for the detected objects are then taken directly from these 3D object detectors that were learned on them. For the ground truth, what we would do is we would pick one of these trained object detectors and then apply, use it to obtain features. For instance, if we have the point group, we can then take the masked points and then obtain features for that. In our earlier work, Scan Refer from 2020, we started out with a fairly simple text encoder. This was just a GRU plus glove embeddings, and we'll see how well this performs. And then just different choices again in the multi-modal fusion. The simplest is to just simply concatenate the two modalities, but nowadays we're in the age of transformers, we would use attention to basically, I guess it's kind of self-attention, but once you have two modalities mixed in, it becomes kind of like cross-attention. So we have this attention and we'll have to see how that changes the performance. For evaluation, we do, this is fairly common, object detection metrics, but we'll do some adaptations for different tasks we do. For the task of localization, what we'll do is we'll compute the intersection over union. So I guess maybe I skipped a step, but basically one thing during training is that you have these predicted boxes versus the ground truth boxes. So first thing you have to do is do some kind of matching so that you can match a ground truth box with a predicted box. But assuming you've done that, what you can do is compute the intersection over union of the two boxes, and then you can use that as a threshold and then compute whatever metric you want. For our case, we'll compute the accuracy at IOU of 0.5. In addition, the other thing we do to evaluate our task, and this is part of the, because we basically, the way we collected data is we took objects and we just asked the people to write descriptions for them. We did do verification that the descriptions were accurate and should only refer to one object in the scene, and this is kind of an assumption that we have in this work. But what we didn't check was whether you needed this full description to identify this object. By this, what I mean is that in some scenes, there is only one refrigerator. And if you could identify, if you could fixate on the fact that this sentence is talking about a refrigerator, you can pretty much ignore the rest of the sentence. So this is what we call unique in the sense that there's only one object of that category in the scene. And then there are harder cases where there's multiple objects of the same category in the scene. For instance, this is a white trash can. It is behind a short white trash can. So in order to figure out which object this sentence is referring to, you have to actually parse and understand the entire sentence versus just saying, oh, it's a trash can. I know exactly which object it is referring to. Okay, so this is the setup for the evaluation metrics. Now let's look at how well the model performs, the different variants we're looking at. If we look at the initial thing so here we're gonna show what happens if we have ground truth versus just using a simple VoteNet. This is again a true object detector, and we can look at using VoteNet features. And this is kind of our initial work where we use VoteNet, and we can compare you doing concatenation and the self-attention. Okay, I have to admit the self-attention was done later, but you can see at least at the point of this, for the detected predicted bounding boxes for VoteNet, the self-attention doesn't matter too much, but it does have a slight improvement in performance. But the main thing you'll notice here is that even if we just focus on this unique set, the performance drops quite a bit. And this suggests that one of the key bottlenecks that we're currently facing right now is just the quality of the object detection. And so this is a question of what happens if we just use a better object detector, right? So again, point group is actually an instance segmentation. So it's actually trained with more supervision than VoteNet, which is just bounding box. So with point group, you are able to actually get much better performance. and both the ground truth performance goes up as well as the detected performance. The other thing we can look at is, and this is a bit more recent work done by one of my students, you can replace the text encoder with a stronger text encoder. Again, nowadays we have these large pre-trained models, for instance, CLIP, which is not only pre-trained, but is trained so that the text and the images are aligned. And right now that doesn't matter, but we'll see when it starts to be important. So if we take CLIP, we can see that if we were to use just the CLIP features, that overall the performance just improves. And it improves much more significantly for the multiple case than for the unique case. So that shows that CLIP is doing something a bit more, being able to disambiguate much better than the GRU with glove embeddings. Now, we've used the text encoder for CLIP. Can we actually also leverage the fact that CLIP is trained such that the text and images are aligned? So here what we do is we then take our detected objects and we want to then take images of it. And this in some ways conceptually is very simple, but it is also sometimes a little bit tricky engineering-wise to do efficiently. And we're happy to say we were able to do this fairly well. We basically have we use PyTorch 3D, and we can incorporate fairly efficient multi-view object renderer based on so basically what we do is we take the detected bounding boxes and we figure out good viewpoints around the object and to render that. And here is just, it's relatively efficient, but there's still a little bit of overhead in the sense that the memory is almost the same, but the time to train goes up by about 25%. So it's not too much. So, and if we do both of this, then we can see our performance improves even more. And you can, our implementation is online if you're interested. And I'm happy to say that through this kind of very simple method, we're actually right now able to be at the state of the art at the scan refer benchmark. And you'll see that there is a whole bunch of other methods as well, including this other work with CLIP and CLIP. I don't know, so I don't know too much about them because they're just on the leaderboard. I don't really know anything, but you'll notice that our method, we use CLIP, they use CLIP, we're much stronger. And then the other thing I want to say is that this is my personal opinion in the sense that sometimes is it an incentive? There's a focus in having very complex methods. So some of these other methods, I think maybe some of them have fallen off the leaderboard, but some of them use fairly complex graph neural networks to do reasoning and such. And what we've been finding is that maybe it's not necessary if you actually pay careful attention to the design choices you make. And yeah, okay. And we've been also extending our work a bit to a more realistic setup. So scan refer currently assumes that whatever description you give it and whatever input thing, there's exactly one object that matches it. And this, I would argue, is not a realistic scenario, because maybe when I said, oh, give me the apple on the table, I just was kind of confused. There was no apple on the table. And in which case you want to be able to handle that, the fact that there was no object that matches. Or sometimes, you know, maybe there's two apples. Which one did you want? So ideally, we would want to have methods that can locate not just one, but be able to figure out, you know, is it 0, is it 1, or is it multiple? And this is something that is ongoing work. So I'm not going to talk about that too much. But let's go back to this idea of taking both, doing the task, both the visual grounding and the captioning task together. And so the nice thing about being able to do it together is that you can then start to have data augmentation. And for for many of these more complex methods, so I will call this one the more complex method, and then after this, I hope to show a slightly better, more simpler model. But here, what we would have is we would have a detector, a speaker, and then, you know, we would basically then, these different components would be then trained independently, and then, and the listener is the visual grounding aspect that I just talked about, and then we will fine tune everything. And one thing you'll notice is that we can basically use through this process, we can actually use the speaker to generate additional captions. So we have during the training process, we have the ground truth where the boxes are, but maybe it'll help to have more descriptions. And so we can use this as a way to generate more data for training the listener. And by doing this, so this work was based on our, not based on the clip-based model, but just on a more basic model with the GRU and the point group. So we start with a little bit lower accuracy. But if we were to do this joint training as well as add additional data, we can actually improve the performance a little bit. Yeah, so, okay. So the message here is that it's good to do two tasks together, and by having data augmentation, it can help. However, that I have to admit that model was not very elegant. And so follow-up work, this is work with Dave in collaboration with Ronghang and Xinei from Meta. And we wanted to explore this more truly unified architecture where we didn't have, you know, the detector and listener being different kind of just different models. Instead, here, again, this is a trend in vision and language. We are going to use transformers. And I think that's really also one thing that's very nice about transformers, where you don't have to say, I use CNNs for my images, and now use RNNs for my language. This, of course, transformers have other great characteristics too, but this is, I think, one of the nice ones where you can just use the same architecture for both modalities, and you can also use it for point clouds as well. Although in this particular case, we're mainly using the transformer for the fusion component, I would say, and also for the language embedding. But for the object detection itself, we're still relying on point group to extract. And part of the reason is just point group is so good. It's just very good. And we're using point group to extract the objects and then taking those objects and then having that features passing into the transformer. But anyways, this is now a unified framework. And now we can start to do maybe a bit of 3D language pre-training, where we would take our architecture and then pre-train it on these text and point cloud pairs, and then fine-tune it on downstream tasks. So during pre-training, then we are not necessarily, so targeted. We have the same set of weights for both tasks, while during fine-tuning, we may have specialized weights. Okay. So again, joint training. So we can, and again, there's different choices of whether you start from scratch or you pre-train, and then the direct task specific training, you would basically have a different set of weights. And I think this is probably not a big finding, but we do show that if you do the, if you do the direct training, then it may be, it can perform fairly well, but if you do joint training, it's better than the single task training. And then we can also pre-train on generated data and then fine-tune our annotated data. And by generated data, what do we mean? So I do think this ability to do either data augmentation or to basically construct data that's, that wasn't humanly annotated is a very powerful idea. So here what we do is we take these objects that are detected in ScanNet, and we can have the 2D frames, and we can then generate captions for these objects in an automated way by using an image captioning system. In this particular case, we chose ClipCap, and you can actually see, so these are some examples of the captions from ClipCap. You can see, like, for some of them, it's kind of good, you know, a bed with a blue blanket and a blue bedspread seems good, but some of them are just kind of poor. This is not a kitchen with a microwave and shelf. It's just some cabinet with a TV in the middle. So it can be good or it can be good, bad, but in the end, even so some of these captions are poor, they can still help. And so here's just a quick chart showing that with these captions, that's the orange line, it kind of improved both the localization and captioning performance as well. And yeah, the effect is a little bit less, but I think we can, this is a direction that's, I think, interesting and can be pursued. So this is this line of work that the localization of objects in 3D. For the last part of my talk, I would like to just highlight again that we are running this challenge as NeurIPS 2023 for home robot open vocabulary mobile manipulation. And this challenge is based on a new data set that we've been building called the Habitat Synthetic Scenes dataset, or HSSD. And this is 211 human-created scenes with over 18,000 different objects. And the nice thing about synthetic scenes is that it allows for different arrangements. This particular data set is using the data exactly as human has created it. But previous work, Poxworth from NeurIPS, this is from AI2, and they have created this huge data set of procedurally generated 3D scenes. That the work is called Poxworth. And here you'll see that the Poxworth scenes is much more sparse than what we have in HSSD. And they were able to show that using their generated scenes, they can improve performance on various embodied AI navigation tasks, such as navigating to a chair, navigating to a couch. We show that with our HSSD data, even so it's a much smaller scale, you can actually potentially improve if you pre-train on our data, you can potentially transfer better to this HM 3D SEM, which is a connection of scanned real world scenes. So, and part of the reason is because the object rearrangement distribution is just more similar to real world scenes. So there is power to having high quality data. And if you have high quality data, you can do with less of it versus having just tons of lower quality data. So for the open vocabulary mobile manipulation challenge, it's a big mouthful, so we call it OVMM. We take this HSSD scenes data set and we combine it with objects from a variety of different data sets to provide this challenge where the goal is we want to have a robot that can move objects from one place to another. And it's the key of this challenge is that it's open vocabulary. So you can have, move toy animal, maybe it's moving picture. So the slots you see, the red, the blue, and the green, which specifies the object, the start receptacle, and the goal receptacle. They are kind of open vocabulary. And here I just show two of the baselines we have. This is the same baseline, but one of them is using ground truth semantics. I'm not going to talk too much about the baseline, but basically the idea is it builds uses object detection. From the object detection, it will build a semantic map of the environment, and then it will go around and then try to locate, for instance, where's the cell phone. Here you can see the cell phone for a bit, to pick that up, and then locate the ending point and then put it away. And one thing that we'll see is that if we replace the ground truth semantics with eidetic semantics prediction, it just can't find the object. It's just kind of lost. Okay. And I want to end my talk with talking about some of the challenges in 3D reasoning with language. So I think we're still very far from fine-grained understanding of text in the grounding of text to 3D. As well as this, for 3D, it's a little bit more complex than dealing with images, in the sense images kind of have a fairly standardized representation of pixels. In 3D, there's kind of all kinds of different representations. Do you work with meshes? Do you work with point clouds? Do you work with voxels? Is any of these representation better than another for reasoning? Maybe, maybe not. And in addition, there's a limited amount of 3D data paired with text, but maybe we can leverage text and image pre-trained models. And maybe we can also develop unified models for language and 3D, similar to those that people are investigating for text. So to conclude, I just want to say there's many challenging 3D and language tasks, and there's a lot of work to be done to effectively integrate all these multimodal information. And there's right now, I think it's an exciting time to be in this field, since there's a lot of recent development, large vision language models, there's 3D generative models are all very exciting. So I think it's a very exciting time to be in the field, and I encourage everyone to participate. Okay.
And again, we'll open up the floor to Q&A. If there's any questions, please go ahead to approach the microphone. And the same for the online participants. If you have any questions, feel free to unmute and talk.
Thanks for your presentation. My question is about the rendering from the point cloud. You mentioned that you render a multi-view from the point cloud.
Yeah.
So is the quality very high? And is the quality very important to forecast, or just the normal?
So the quality is not very high. I would say the quality is fairly low, but it seems that even so the quality is not very high, it can help in the performance. And so there's a question of if we render more high quality. So the quality is not high for two reasons. One is the point cloud, and it'll be dependent upon, how dense the points are. And the other is the reconstructed mesh is also, incomplete. So it's not high in both of those senses. And so it's interesting. Currently, I work with these scanned data, but it's an interesting question of what happens if we work with this HSSD data set I presented, the synthetic data set. Then you can render high quality, but in order to render from the mesh, then it's possible, but you need to probably do a little bit more engineering work to get it to be efficient. Yeah.
Actually, your reference provide excellent quality for different of the rendering. I'm not sure if they provide better than the quality. It is very helpful for the following task.
Yeah. I suspect it would be, but also again, because this task is based on these kind of large objects. So if we start to talk about, it really depends on, if we start to talk about, look, trying to find a pen on something, and maybe if it's a shiny pen or stuff like that, depending on the attribute, then I think the rendering quality will be very important. Yeah.
And my second question is about the additional information from another image in addition to the original point cloud. So the point cloud is also colored point cloud.
It's colored, and it's not just colored. We actually have multi-view features on top of the colors. So that means that there was already a path where there was multiple multiple views that was, and then a innet was run to accumulate features for the point. So it's not just the colors, but yeah, yeah.
Really comprehensive data formats. I mean, it seems that the point cloud provide enough information to the point cloud. So what kind of additional information does
So
provide?
yeah, so I think there's two parts to that. One is that is it the information or is it the encoder that we're using? So for instance, the clip.
Better, image encoder.
Yeah, so yeah, like clip is like, and it's not so much about the architecture, but the fact is pre-trained on a lot of text and image pairs. And so if we're just using point clouds, then without doing this image it doesn't have to be multi-view, but these image features, then we can't leverage these pre-trained image encoders.
Well, the challenge I see from the seeking your insights, right? So since the processing of doing the visual and text alignment in the scan refer data set, you use clip and other pre-trained visual models. So these pre-trained visual models are essentially trained on 2D images, right? I understand there is a huge challenge of lack of 3D data to train such a similar large representation model. But if we directly use clip, then isn't it will be influenced by the fine-grained kind of noise that you reconstruct the 2D image back from the 3D data, and would that affect essentially bring the performance challenge to the ultimate system?
Yeah, so I do think people are starting to explore using clip as a bridge, and not just clip, any like vision language model as this bridge between 3D and text, or for open vocabulary understanding of 3D. People are starting to do that, but I think right now it's very limited. So I think there's a lot of work that can be done to actually see. I'm sure that we're dropping a lot of performance on the way, in the sense that the rendering quality is not very good. There may be a domain gap between what clip saw versus the, the kind of visuals we're giving it. And yeah.
And also we need the direct depth information.
Yeah, and it's not utilizing the depth information right now, and we could be utilizing that. And there's a question about, if we have the depth information, how should we use it? Should we, like, I think in previous work, I don't know how much people are using depth right now, but previously, with ResNet, people would take the pre-trained backbone and then just cut off like maybe the bottom layer, the closest to where the depth is, and the rest of it is still helpful. So clip can also potentially be like that. Yeah.
Thank you. All right. Let's I would just like to remind the poster presenters, our poster session starting from 3 to 4 p.m. at